Welcome to the wonders of our galaxy. Picture this: an immense system filled with shimmering clouds of gas and a staggering 100 billion stars. Yes, that's right. We're diving into the Milky Way. Did you know it takes a staggering 100,000 years for light to travel across our entire galaxy? The heart of it all is hidden away in the constellation of Sagittarius, shrouded by mysterious clouds of dusty gas that float among the stars. How fascinating is that? Let's dive into the intriguing structure of our galaxy, which is made up of two main parts: the disk and the halo. It's a cosmic journey you won't want to miss. Imagine gazing at the Milky Way, our stunning cosmic panorama. This breathtaking disk stretches across roughly 100,000 light-years with a thickness that's just a fraction of that diameter. It's a vast and mesmerizing sight that captivates the imagination. The disk is made up of stars and interstellar gas, holding more than half of the visible mass of our galaxy. It's a fascinating aspect of our universe that truly captures the imagination. The gas makes up about 1/10 of the matter in the disk, while the dust contributes around 1% or more of the gas's mass. Imagine the stars, gas, and dust disks swirling around like a massive carousel at the heart of our galaxy. It's a mesmerizing dance happening right in the nucleus of the Milky Way. Did you know that most of the stars we gaze at in the night sky are part of a vast disk? These celestial wonders are often separated from their closest companions by just a few light years. Isn't that fascinating? Did you know that our Sun is a staggering 30,000 light-years away from the galactic center? It zips through space at an impressive speed of 300 kilometers per second. And get this: it takes a whopping 200 million years to complete just one orbit around the galaxy. How wild is that? Throughout its incredible lifespan, the Sun has made an astonishing 25 trips around our galaxy. Imagine a massive spherical halo perfectly centered around the galaxy's nucleus, stretching an astonishing diameter of about 200,000 light-years. How mind-blowing is that? The heart of the halo is where we find the nuclear bulge of the disk, a fascinating feature worth exploring. Beyond the atomic bulge, we find the halo, which is made up of low-density gas, stars that are spaced out, and around 120 globular clusters. It's a fascinating area of our galaxy that holds many secrets. Imagine a dazzling collection of hundreds of thousands of stars packed tightly together. This is what globular clusters are all about. These stellar wonders travel in elliptical orbits around the heart of our galaxy, creating a mesmerizing cosmic dance that captivates the imagination. The halo remains stationary while the disk spins around it. Picture this: a flat disk, bursting with gas and dust, spins energetically, while a spherical halo, lacking in those materials, rotates at a much more leisurely pace. Fascinating, right? In 1942, Walter Baade made an exciting discovery. He found that each region of the universe is home to a unique type of star. There are two fascinating types of stars that astronomers categorize as populations 1 and 2. The disk is home to a vibrant mix of population 1 stars, while the halo showcases the more ancient population 2 stars. It's a fascinating contrast that highlights the diverse stages of stellar evolution in our galaxy. Let's dive into the fascinating world of population 1 stars, also known as the disk stars. These are the stars we've been exploring together. The Sun is a star that shines brightly in our cosmic neighborhood. These stars are typically much younger than the galaxy itself. They are composed of a variety of chemical elements that are heavier than helium, accounting for approximately 1 to 2% of their total mass. Gas clouds swirling in the disk are the cosmic nurseries where new stars are born. When stars reach the end of their lives, they create a spectacular legacy by ejecting heavy elements into the cosmos. Every new generation of stars is born with a rich legacy of heavy elements, passed down from their stellar predecessors that have gone supernova. As time goes on, the gas reservoir in the disk diminishes, while the concentration of heavier elements rises. In the vast expanse of interstellar space, heavy element atoms collide and bond, creating tiny dust-like grains that float through the cosmos. These tiny dust grains, measuring less than 1 micron, that's 1/100th of a millimeter, are fascinatingly small, yet perfectly sized to absorb visible light. Imagine tiny dust grains surfing on atomic winds, journeying through the vastness of space. They gather in the mysterious dark clouds, the very places where new stars are born. Isn't that fascinating? The halo is home to population 2 stars, known for their abundance of globular clusters and striking nuclear bulges. The gas density in the halo is incredibly low, making it nearly impossible for new stars to form. Most of the stars we see in the halo were born ages ago, back when our galaxy was still in its youth. These celestial wonders are believed to be between 8 and 15 billion years old, originating from clouds of hydrogen and helium gas that were nearly devoid of heavy elements. It turns out that planets can't just spring up from hydrogen and helium by themselves in those halo stars. They won't be hosting any planetary systems either. In the younger population of the universe, stars emerged from a mix of hydrogen and helium, enriched with heavier elements. These heavy elements clump together into dust grains, which then coalesce to form meteoroids, ultimately leading to the creation of planets and the cores of massive gas giants. It's a fascinating journey of cosmic evolution. It's likely that many stars, especially those like our Sun, have planets orbiting them, and these intriguing worlds could be the very places where alien life might thrive. In the heart of our galaxy, known as the nuclear bulge, you'll find a fascinating blend of disk stars, often referred to as Population 1, alongside the older halo stars, known as Population 2. It's a cosmic melting pot that showcases the diverse stellar life in our universe. While it's easy to imagine 2 entirely separate groups, young disk stars and old halo stars, with the former being rich in heavy elements and the latter lacking them, it's essential to recognize that many intermediate populations bridge these 2 categories, exploring the fascinating world of star clusters and the incredible distances that separate them. There are 2 fascinating types of star clusters: open clusters and globular clusters. Open clusters in the disk are fascinating loose groupings of young population I-stars, showcasing the beauty and dynamism of our galaxy. Imagine clusters packed with hundreds of stars, often hanging out with gas clouds for a few million years, just like the stunning Pleiades cluster. It's a cosmic party you won't want to miss. Globular clusters are fascinating cosmic formations, primarily located in the halo and nuclear bulge of galaxies, and they take on a stunning spherical shape. Imagine vast cosmic structures stretching across about 100 light-years, filled with hundreds of thousands of ancient Population 2 stars. It's a breathtaking glimpse into the universe's history. Both open and globular clusters play a crucial role in helping astronomers gauge distances in the universe. Parallax measurements help us uncover the distance to a star that's just a hop, skip, and jump away in our cosmic neighborhood. To determine how far away a star is, we compare its brightness to that of a similar star that's closer and has a known distance. This method helps us unlock the mysteries of the universe. You'll find that comparing clusters leads to much better results than just looking at single stars. In a star cluster, you'll find that all the stars share a similar age, a comparable mix of chemical elements, and are roughly the same distance apart. It's fascinating how these celestial bodies come together in such harmony. Imagine a dazzling cluster filled with stars, each shining with its unique brightness and temperature. we capture this cosmic family reunion by creating an HR diagram, where we plot the apparent brightness of each star against its surface temperature. It's like a celestial snapshot that reveals the diverse personalities of these stellar beings. Every star shines brightly along a clear and defined main sequence. When we dive into the family portraits, or HR diagrams, of various clusters, we uncover their relative distances fascinatingly. So if the main sequence is in one, the HR diagram shows that it's 4 times fainter than the main sequence in a second diagram, while the first cluster sits at twice the distance of the second. Fascinating stuff, right? This approach is super practical, especially when adjustments take into account the variations in the element composition of the clusters. Did you know that the closest open cluster to us is the Hyades? It's a fascinating topic to dive into. Let's dive into the fascinating world of the Bull in the Taurus constellation. This stellar formation boasts at least 200 stars, all shining brightly from a distance of 140 light-years. How cool is that? This fascinating cluster is so close that we can measure its distance using parallax techniques. The distance is also determined using the moving cluster method. Did you know that the Hyades cluster is moving away from us? It's fascinating to think about how it seems to be slowly shrinking. By using the Doppler effect to measure its velocity and observing its apparent rate of shrinking, we can uncover the distance to this intriguing cluster. Join us as we dive deeper into this cosmic mystery. By leveraging the known distance of the cluster, we can use main sequence fitting to uncover the distances of other open clusters that are out there. There are several open clusters located at known distances that feature Cepheid stars. These fascinating pulsating stars follow a captivating period luminosity law, where the pulsation period is intricately linked to their luminosity. Did you know that Cepheids shine with a brilliance that's about 10,000 times greater than our Sun? These incredible stars can be spotted from vast distances, making them truly fascinating objects in the universe. Using the brilliant Cepheids as our measuring tools, we're now able to make significant leaps in measuring the distances to nearby galaxies. The Hyades cluster is truly fascinating. Its distance plays a crucial role in shaping our understanding of the size of our galaxy, and even influences how we perceive other galaxies and the universe as a whole. It's a key piece of the cosmic puzzle. Determining astronomical distances is a fascinating challenge filled with uncertainties, especially when it comes to accurately accounting for how starlight is absorbed by dust in the vastness of interstellar space. In the early 1900s, astronomers began to theorize that the mysterious dark matter floating in the vastness of space might be absorbing starlight as it travels between the stars. In 1930, Robert Trumpler from the Lick Observatory made a groundbreaking discovery that unveiled this obscuring medium. The mysterious obscuration we see is actually due to tiny grains of matter, or dust, scattered throughout the disk, especially within those intriguing gas clouds. Did you know that about 1 to 2% of the mass of interstellar matter is made up of dust? It's a fascinating detail that highlights the universe's complexity. Trumpler discovered that the intensity of starlight diminishes significantly, being cut in half for every 3,000 light-years it travels through the disk. Fascinating, right? So, a disk star located 6,000 light-years away appears to shine with only a quarter of its actual brightness due to absorption effects. In the disk, we can observe stars through telescopes that are thousands of light-years away. However, as we look further out, especially towards the galactic center, those stars start to fade from our sight. The dust creates a mysterious fog-like layer in the disk. As we gaze at the stunning plane of the Milky Way, we can spot a multitude of nearby stars. But intriguingly, there are no galaxies in sight. When we gaze out from the plane of the Milky Way, it's fascinating to notice the scarcity of stars and the abundance of distant galaxies. It's a cosmic perspective that puts our place in the universe into context. While this conclusion applies to visible light, it doesn't hold for infrared and radio signals which can cut through the fog. Wavelengths that are larger than dust grains pose a challenge when it comes to absorption or scattering. It's a fascinating topic that dives into the complexities of light and matter interaction. Why does red light cut through fog better than blue light? Let's dive into this fascinating phenomenon. Did you know that long infrared and radio waves can uncover the hidden inner regions of our galaxy? It's fascinating how visible light can obscure so much from our view. When we take a closer look at these longer wavelengths, we discover that the nuclear bulge stretches an impressive 10,000 light-years from the nucleus. It's a fascinating and intricate system filled with swirling gas and a multitude of stars, revealing the dynamic nature of our universe. In the heart of this region, you'll find a fascinating mix of old and young stars packed closely together, far more so than what we see in our corner of the galaxy. It's a stellar neighborhood like no other. In the heart of the nucleus, several powerful radiation sources have led astronomers to speculate about the presence of one or more massive black holes lurking within. It's a fascinating mystery that keeps scientists on the edge of their seats. These incredible creatures of the deep may not shine on their own, but when gas falls and gets compressed, it heats up and can light up the darkness. One of the most fascinating features of countless external galaxies is their mesmerizing spiral-like shape. Research into how gas and stars are spread throughout the disk reveals that our galaxy boasts a fascinating spiral structure. Picture this: spiral arms reaching out from a glowing nuclear bulge, bursting with vibrant young stars and dazzling gas clouds. It's a cosmic spectacle that captivates the imagination. Have you ever wondered why we can spot the stunning spiral structure of external galaxies? It's all thanks to their vibrant spiral arms, which are packed with bright stars and gas clouds. Meanwhile, the other stars in their disks, though less noticeable, are spread out in a more uniform pattern. Fascinating, right? Initially, astronomers believed that the spiral arms of galaxies were home to a consistent set of stars, with both the stars and the arms moving in sync within the galactic disk. However, this concept went against what we could see. The stars at the heart of the galaxy spin around the galactic center much faster than those on the outskirts, just like how the inner planets zip around the sun quicker than their outer counterparts. Fascinating, right? So, the arms would gradually twist tighter and tighter, creating a more intense spiral as they go. Every 100 million years or so, each spiral arm would add another twist to its cosmic dance. Interestingly, many spiral galaxies that are billions of years old showcase just one or two turns in their structure. The intriguing winding problem, as it came to be known, found its solution thanks to the brilliant Swedish astronomer Bertil Lindblad, who introduced the fascinating density wave theory. Imagine this. Spiral arms in galaxies are like ripples in a pond, moving through the cosmic disk, just like sound waves travel through the air. That's the essence of the density wave theory. Imagine each spiral arm as a mesmerizing ripple, gracefully swirling around the disk while maintaining its stunning shape. Spiral arms are fascinating areas where gas density is significantly higher. Did you know that the higher gas density in galaxies plays a crucial role in triggering star formation? It's a fascinating process, even if we don't fully understand all the details yet. Plus, those stunning spiral arms are home to a plethora of newborn stars just waiting to shine. It takes millions of years for gas and stars to journey through a spiral arm of the galaxy. It's fascinating to think that the most brilliant stars in our universe shine brightly for just a few million years. By the time they drift away from a spiral arm, their incredible journey has already come to an end. There's a noticeable lack of bright stars and their vibrant gas clouds hanging out between the spiral arms. That's right. Spiral arms stand out, And it's all thanks to the presence of the brightest stars shining within them. The arrangement of older stars in the disk remains undisturbed primarily by the passing spiral ripple. When we look at their combined light, it reveals a subtle spiral pattern that's truly fascinating. The far-off galaxies previously referred to as nebulae are millions of light-years apart from each other. They stretch out in infinite numbers, each one a breathtaking celestial city of stars, gracefully gliding through the vastness of space. Many have unique characteristics that help astronomers categorize them into either elliptical or spiral galaxies. Elliptical galaxies, often referred to as ellipticals, showcase a fascinating oval shape. While some may appear spherical, the majority resemble oblate spheres, adding to their unique charm in the cosmos. Their outer regions blend into the unknown, and they lack distinct borders. You'll find that a lot of ellipticals, especially the larger ones, feature strikingly bright centers. These regions are nearly devoid of gas and dust, the essential ingredients for new star formation, and are primarily made up of ancient population II stars. Elliptical galaxies come in all shapes and sizes, from tiny dwarf galaxies that are only slightly bigger than globular clusters, to extraordinary giants, like M87. Some of these supergiant galaxies are mind-blowingly massive, hundreds of times the mass of our own Milky Way and stretching across a staggering 500,000 light-years in diameter. Giant ellipticals, often referred to as type E0, pronounced E0, have a striking spherical shape and are known for their brilliantly bright nuclei. In contrast, dwarf ellipticals are characterized by their absence of these bright nuclei, making them quite different in appearance. Did you know that more than 60% of galaxies out there are ellipticals? And guess what? Most of those ellipticals are dwarf systems. How fascinating is that? Spiral galaxies, often referred to as spirals, are fascinating cosmic structures that include disks filled with young, vibrant population I-stars, alongside halos that host the older, more mysterious population II stars. Join us as we dive into the wonders of these celestial formations. Picture this. The galaxy, with its stunning spiral arms elegantly winding around the vibrant central nuclear bulges. It's a cosmic dance that captivates the imagination. Spirals come in two exciting flavors. The classic normal spirals, known as S, and the intriguing barred spirals referred to as SB. Normal spirals come in three fascinating types. The SR, which boasts large nuclear bulges and tightly wound arms. The SB, featuring smaller nuclear bulges and a bit looser arms. And the SC, showcasing the smallest atomic bulges with the least tightly wound arms. Each type offers a unique glimpse into the beauty of the cosmos. Did you know that our galaxy, along with the Andromeda Nebula, falls into the fascinating category of type SB? It's a captivating topic that sparks curiosity about the universe. Did you know that around 1/3 of all spiral galaxies are the barred type? It's a fascinating fact that adds depth to our understanding of the universe. These galaxies are categorized into three types: SBA, SBB, and SBC. This classification is based on the size of their nuclear bulge and the tightness of their spiral arms, just like in the case of regular spiral galaxies. Picture a vibrant central bar that extends beyond the nuclear bulge, seamlessly linking up with the spiral arms. This is what sets them apart. This bar is made up of stars and gas. Yet the reasons behind spirals are bursting with gas that gathers in their disks, fueling the incredible birth of new stars. In contrast to ellipticals, these galaxies showcase a vibrant mix of stars across different ages. You'll find the youthful I stars shining brightly in their disks, while the older II stars reside in their halos and nuclear bulges. creating a fascinating tapestry of stellar evolution. Unlike ellipticals, they don't showcase the incredible variety of masses and sizes. Typically, their masses fall within the range of 10 to 1,000 billion solar masses. Did you know that most of the dazzling galaxies we see out there are spirals? It's a fascinating topic that sparks curiosity. Ellipticals stand out as the most abundant and vibrant galaxies in the universe, showcasing an intriguing array of rare giants and even more elusive supergiants. At the iconic Mount Wilson Observatory, Edwin Hubble created an incredible diagram of galaxies that resembles a tuning fork, fascinatingly showcasing the universe's structure. Imagine a fascinating sequence where ellipticals line up in one branch, showcasing a stunning progression of increasing ellipticity. Meanwhile, regular and barred spirals create their captivating sequences in two parallel branches, each with its unique charm. It's a cosmic dance of galaxies that you won't want to miss. Imagine a diagram that sorts galaxies based on how they look. Take an E0 galaxy, for instance. It could be a perfectly spherical system or a flattened elliptical one that we see head-on. Fascinating, right? At the crossroads of the three branches, Hubble introduced the fascinating S0 galaxies, which blend the characteristics of both elliptical and spiral galaxies. These fascinating celestial objects are disc-shaped and have a spiral-like appearance. Yet they don't contain gas or exhibit an actual spiral structure, giving them a striking resemblance to elliptical galaxies. Imagine spirals that are perfectly polished and free from any gas and dust. They're stunning to behold. In the tuning fork diagram, we see a fascinating trend. The amount of interstellar gas in galaxies ramps up as we move from ellipticals to spirals, going from left to right. It's a captivating journey through the cosmos. In elliptical galaxies, gas is scarce. The same goes for S0 galaxies, but as we move into spiral galaxies, the gas content starts to ramp up, especially from SA and SBA types to SC and SBC. It's a fascinating progression to explore. The impact of rotation stands out as we transition from elliptical galaxies to spiral ones. Initially, the idea was that galaxies evolved from left to right on the tuning fork diagram, which is why we refer to those on the left as early type and those on the right as late type. Then the perspective shifted to suggest that they evolved from left to right. However, current thinking among astronomers leans towards the notion that significant evolution along this diagram is unlikely. Instead, the fundamental characteristics that set ellipticals apart from spirals were likely established right at their inception. These fascinating celestial bodies have an irregular appearance and are classified as irregulars, denoted by the abbreviation IRR. Did you know that our closest galactic neighbors, the Small and Large Magellanic Clouds, are fascinating examples of irregular galaxies? Please tune in to explore their unique characteristics and what makes them stand out in the cosmos. These galaxies showcase fascinating shapes reminiscent of those found in Halton Arp's Atlas of Peculiar Galaxies. Their unique looks often stem from tidal interactions with nearby galaxies, creating a captivating cosmic dance. Did you know that galaxies aren't just floating around randomly in space? Instead, they gather together in clusters of various sizes, creating fascinating formations in the universe. Picture this: massive clusters of galaxies resembling giant globular clusters of stars, all taking on a stunning spherical shape. It's a cosmic spectacle that truly captivates the imagination. Their galaxies gather in the heart of the cosmos. These groups are incredibly wealthy, boasting a vast membership and housing thousands of galaxies, predominantly of the elliptical and S0 varieties. Supergiant ellipticals, those massive giants of the universe, have likely reached their incredible size by devouring smaller galaxies, and you can often find them hanging out in the heart of galaxy clusters. Regular clusters usually span about 10 million light-years across and feature soft, undefined edges. Imagine vast expanses filled with intergalactic gas alongside dazzling stars and globular clusters as galaxies zoom by at mind-blowing speeds, often surpassing 1,000 kilometers per second. It's a cosmic race like no other. Imagine the powerful winds of intergalactic gas racing through these rapidly moving galaxies, forceful enough to sweep away their precious interstellar gas. This suggests that S0 galaxies within major clusters were once typical spiral galaxies, and intergalactic winds have stripped away their gas. Every other cluster of galaxies out there is irregular. These clusters come in a wide range of richness, and are much more common than the rare regular ones. These fascinating structures don't exhibit spherical symmetry or strong central condensation, and they host a diverse mix of galaxy types. The notable irregular clusters look clumpy, almost like they've fused into larger groupings of smaller clusters. Irregular clusters can vary widely, from massive gatherings of thousands like the impressive Virgo cluster to smaller collections of just a few dozen, such as our very own local group. Imagine small irregular clusters known as groups that stretch across a staggering 3 million light-years. How wild is that? Did you know our galaxy is part of the local group? It's a fascinating little cluster made up of around 20 galaxies, and if we include the smaller systems that resemble tiny globular clusters, the number keeps growing. Venture into the vastness of space, reaching far beyond our familiar surroundings. Did you know there are countless other groups of galaxies out there? It's mind-blowing to think about the vastness of the universe. Let's dive into the fascinating world of the cosmos. Did you know that the nearest significant cluster out there is the irregular Virgo cluster? It's located about 70 million light-years away. How incredible is that? Did you know that the closest regular cluster to us is the Coma cluster? It's located about 450 million light-years away. Pretty mind-blowing. Did you know that galaxies thin out a bit after around 100 million light-years? It's fascinating to discover that they come together to form massive superclusters. Let's dive into this cosmic phenomenon. Did you know that the local cluster we call home is centered around the fascinating Virgo cluster? It's part of the even more incredible Virgo supercluster. Figuring out how far away galaxies are is super crucial in the world of cosmology, but it comes with its challenges. By looking at the brightness of the brightest stars in nearby galaxies, we can figure out how far away those galaxies are. It's a fascinating way to explore the universe around us. The dazzling Cepheids play a crucial role in mapping out our nearby extragalactic neighborhood. Determining the distances of galaxies that are further out can be quite a challenge, and the uncertainty only grows as we look deeper into the cosmos. The brightness we see from the most luminous stars and globular clusters serves as a fascinating distance marker, extending to about 80 million light-years away. The striking size of brilliantly glowing gas clouds and the dazzling brightness of supernovas draw us into the depths of the universe. Once you venture beyond 100 million light-years, the distances become a cosmic mystery, with uncertainties that could swing by a factor of 2 or even more. It's a wild ride through the universe. We now have to look to galaxies as our guides for measuring distances in the universe. What we observe in space is a glimpse into the distant past, showcasing galaxies that were once younger and vastly different from what we know today. Taking this into account, along with the potential for evolutionary changes, really ramps up the challenges we face when trying to figure out the distances to those far-off galaxies. Did you know that most galaxies are home to ancient population 2 stars? These stellar giants are billions of years old, with the majority having formed aeons ago. It's a fascinating glimpse into the universe's history. The density of matter in intergalactic space has dropped to such a low level that it's no longer capable of forming new galaxies. In a galaxy like ours, the average density of matter is surprisingly low, sitting at just 1 hydrogen atom per cubic centimeter. Fascinating, right? Imagine a scenario where all stars fade away, transforming into gas that expands across a vast sphere measuring 100,000 light-years in diameter. This fascinating concept leads us to a unique density outcome. This astonishing figure is about 1 million times denser than the average matter we find in the universe. Can you believe that? As the universe expanded, it grew thicker, leading to galaxies clustering closer together in an intriguing cosmic dance. 5 billion years ago, as our solar system came into existence, the universe was a very different place. Its average density was about twice what we see today. And if we rewind the clock another 5 billion years, galaxies were much closer together, with an average separation distance that was only half of what it is now. The universe's density was a staggering 8 times greater than it is today. Way back when the universe was packed with more than 1 million times the density we see today, galaxies, as we know them, couldn't exist. They would have been crushed under that immense pressure. They unite in truly mind-blowing ways in a universe that's even denser than galaxies themselves. Galaxies began to take shape in a basic form during a time when the expanding universe had an average density of fewer than 1 hydrogen atom per cubic centimeter. Hey there, cosmic explorers. Did you know that galaxies began their journey in an ever-expanding universe more than 13.8 billion years ago? It's mind-blowing to think about the vastness of time and space. Many theories about how galaxies formed begin with tiny fluctuations in density from the very early universe. The density fluctuations expand and ultimately evolve into proto-galaxies. Imagine P as our baseline density, and now picture 8P as a tiny twist in that density. It's like adding a little spice to the mix. In the early universe, both P and 8P experience a decrease as it expands, but it's interesting to note that 8P decreases at a slower rate than P. So the critical ratio 8P equals P, which we refer to as contrast density, is on the rise and keeps getting stronger. Initially, the contrast density 8P equals P is incredibly small, less than 1/1,000,000,000%. However, as 8P equals PE increases and approaches a value close to 1, we enter the exciting stage of proto-galaxy formation. Imagine a cosmic dance of hydrogen and helium gas, where these elements, born from the very fabric of the early universe, come together in masses that can reach from millions to trillions of solar masses. It's a fascinating glimpse into the building blocks of our universe. These fascinating gas concentrations, often referred to as globes, have been expanding at a slower pace than the universe itself, leading to an intriguing widening of their separations. At some point, every world reaches its peak and starts to shrink. Let's dive into the fascinating process of how these collapsing gas globes could have transformed into galaxies. Let's dive into an intriguing scenario about how a massive galaxy might come into existence. Initially, a gas globe displays a relatively uniform density throughout its volume. When a world reaches its peak size of around, imagine a vast expanse stretching 500,000 light-years across, where the density shifts and changes, no longer uniform. It's a cosmic wonder that sparks curiosity and awe. Around this period, we start to see the formation of the earliest population 2 stars in the central region, where the density is at its peak. The most brilliant of these first-generation stars undergo a swift evolution, culminating in spectacular supernova explosions that blast out gas rich in heavy chemical elements. At this moment, the entire gas cloud is starting to collapse under the pull of its gravity, creating an incredible cosmic spectacle. The collapse unfolds over an astonishing span of hundreds of millions, even billions of years. In the heart of galaxies, stars are constantly being born, and the most brilliant among them shines for just a few million years. So, the gas falling into the proto-galaxy is gradually being packed with heavy elements. It's crucial to recognize that once stars are born, they stop being part of the overall collapse of the proto-galaxy. This fascinating process shapes our universe in ways we are just beginning to understand. Did you know that each newborn star starts its journey by moving inward? But here's the twist. After its formation, it settles into an elliptical orbit, maintaining a consistent average distance from the center. Fascinating, right? Imagine a stunning visual of a collapsing proto-galaxy. A fascinating concept first introduced back in 1962 by the brilliant minds of Olin Egan, Donald Lyndon Bell, and Alan Sandage. In this cosmic drama, the central region transforms into a vibrant swarm of population 2 stars, captivating our imagination and sparking curiosity about the universe. Imagine a massive swarm of stars, all clustered together in a roughly spherical shape. Our galaxy, the Milky Way, stretches an astonishing 100,000 light-years across. Isn't that mind-blowing? So the core of the proto-galaxy has transformed into what we now recognize as the galactic halo. As the stars twinkle above, the remnants of the collapsing proto-galaxy cascade down, creating a mesmerizing cosmic spectacle. Welcome to the fascinating world of the outside-in theory of galaxy formation. Picture this. The core of a proto-galaxy creates a halo, while the outer layers spiral inwards, ultimately shaping the nucleus and disk of a brand new galaxy. It's a cosmic dance of formation. Which galaxy's infalling gas plays a crucial role in deciding if it's a spiral or elliptical galaxy. Imagine a fascinating proto-galactic globe of gas, spinning uniformly in the vastness of space. The outer regions spin faster than the inner sections. Once again, we witness the heart of the world morphing into a dazzling swarm of stars. Thanks to the core's slow spin, this celestial display takes on a nearly perfect spherical shape. Picture this. As the gas from the outer regions spirals inward, it picks up speed, much like a ballet dancer who spins faster when she brings her arms closer to her body. It's a captivating dance of physics in the cosmos. The falling gas gathers up those heavy elements that were kicked out before, playing a crucial role in sparking the birth of new stars. These exciting new stars sit right in the middle between population I and population 2 stars. And guess what? Their distribution in space is way less spherical compared to those of first-generation stars. How cool is that? The gas that remains can't collapse to the center due to its rotation. Instead, it transforms into a swirling disk of gas, rich in hydrogen, helium, and a mix of heavier elements expelled from halo stars. Exciting news in the cosmos. We're witnessing the formation of population 1 stars in the swirling, gaseous disk. Stay tuned as we explore this stellar phenomenon. However, the dynamics of rotation and the influence of magnetic fields create substantial barriers to star formation, resulting in the birth of only a handful of stars each year. In a stunning cosmic event, the massive gas globe has imploded, leading to the formation of a breathtaking spiral galaxy. What sparks the initial rotation? It's still a mystery. These gas giants are tugging at each other, spinning into motion through their gravitational dance. Or perhaps those early universe ripples had a twist to them, right from the start. No matter which theory you lean towards, it's clear that some proto-galaxies spin with more vigor than their counterparts. Imagine a swirling globe of gas spinning at breakneck speed. Just like in the past, the first-generation stars are born in the heart of the galaxy, while the birth of new stars helps to use up the gas that's flowing in from the outer regions. However, the infalling gas currently lacks sufficient rotation to form a massive disk of swirling gas. The gas keeps dropping and is constantly being used up by the process of star formation. The gas that makes it through gathers at the center and forms the nucleus. We've witnessed the spectacular collapse of the original gas globe, leading to the birth of a massive elliptical galaxy. The rotation may not have been enough to create a gigantic, gaseous disk. Still, it played a role in shaping the moderately flattened distribution of stars that we observe in many elliptical galaxies. The initial rotation and density in proto-galaxies play a crucial role in their development. The rate at which stars are born is all about gas density. More density means stars are popping up faster than ever. Imagine a proto-galaxy that boasts a higher density emerging from the cosmic dance of the expanding universe at an earlier stage. In this scenario, stars are born at a faster pace, and any infalling gas doesn't stick around long enough to form a disk or a nucleus. Could this theory be the key to understanding the formation of small ellipticals? Let's dive in. In small, low-mass galaxies, the gas ejected from the first-generation stars never has a chance to mix back in with later stars, as all the stars tend to form around the same time. Isn't that fascinating? The ejected gas may hang around for a while before being swept away by powerful galactic winds. Let's dive into the fascinating world of astronomy. We can explore the origins of those massive cosmic structures in three intriguing ways, exploring the fascinating world of radio galaxies and quasars. Back in 1931, a groundbreaking discovery was made by Carl Jansky at the Bell Telephone Laboratories when he picked up radio signals emanating from our very own Milky Way galaxy. This thrilling discovery has captured the spotlight and generated a buzz everywhere. Imagine tuning into a radio program where the announcer invites you to experience something truly out of this world. I want you to hear for yourself this radio hiss from the depths of the universe. Back in 1938, radio engineer Grote Reber made an incredible discovery, picking up radio signals from our very own Milky Way. He found that these signals were strongest, coming from the galactic center and iconic constellations like Cygnus and Cassiopeia. It's a fascinating journey into the cosmos that you won't want to miss. In the exciting early days of radio astronomy following World War II, hundreds of radio sources were uncovered, and optical astronomers stepped in to identify the visible counterparts of many of these fascinating discoveries. So, here's the scoop. Taurus A, the most powerful radio source we've spotted in the Taurus constellation, turned out to be the Crab Nebula. This wild and chaotic cloud of gas was created by the epic supernova that exploded back in 1054. Cygnus A, also known as 3C405, is a fascinating giant galaxy that stands out with its unique, disturbed appearance, located a staggering 1 billion light-years away from us. Among the most intriguing discoveries in the universe are the optically identified radio sources, particularly the galaxies. Take Cygnus A, for instance. This incredible radio galaxy emits millions of times more energy in radio waves compared to your average galaxy. It's a mind-blowing glimpse into the power of the cosmos. When we look at radio galaxies captured on photographic plates, we often see striking bright central regions, along with fascinating protruding jets like those in M87 and delicate wispy extensions that add to their allure. Imagine the most powerful radio galaxies out there blasting out more energy in radio waves than we can see in visible light. These cosmic giants are often found in rich clusters of galaxies, showcasing their impressive elliptical shapes. Did you know that fast electrons zipping around in helical paths within magnetic fields emit radio waves? It's a fascinating phenomenon that reveals so much about the universe around us. Get ready to dive into the fascinating world of high-energy synchrotron accelerators. These incredible machines generate waves known as synchrotron radiation. It's a thrilling topic that showcases cutting-edge science and technology. Radio galaxies unleash a torrent of high-energy electrons scattered across their radio-emitting areas in a fascinating and not entirely understood manner. Exciting advancements in radio astronomy are opening up new possibilities, allowing us to dive deep into the intricate structures of radio sources like never before. Many sources feature a fascinating double structure emitting radio waves from expansive components positioned on opposite sides of the source. It's a captivating phenomenon that grabs your attention. The two components, or jets, stretch out to incredible distances, reaching hundreds of thousands, and, in some cases, even millions of light years. It's mind-blowing to think about how far they go. The incredible energy emitted by the jets comes straight from the galaxy, likely stemming from its very core. Did you know that at the heart of many radio galaxies lies a dynamic nucleus? This central region is a powerhouse of radio emissions, featuring two distinct components that are just hundreds of light years apart. It's a fascinating glimpse into the universe's most energetic phenomena. So let's dive into the fascinating world of radio sources. There are two main types: extended and compact sources. And get this, some, like Cygnus A, actually fall into both categories. How cool is that? Martin Rees from Cambridge University has proposed an intriguing idea. The collective energy emitted in waves and particles from countless pulsars at the heart of a galaxy is funneled out in two opposing directions. Fascinating, right? These powerful beams unleash their energy, spreading out over vast areas that emit radio waves. One fascinating theory put forth by Soviet astronomers and Philip Morrison from MIT suggests that the gas at the core of a galaxy can contract, leading to the formation of one or more supermassive black holes. These cosmic giants not only rotate, but also possess powerful magnetic fields, adding another layer of intrigue to our understanding of the universe. Imagine spinners that are millions of times more massive than our Sun. These colossal pulsars are like cosmic giants, sending out powerful beams of energy into the vastness of intergalactic space. It's a mind-blowing phenomenon that you won't want to miss. Exciting advancements in various branches of astronomy quickly surpassed these initial concepts. Quasars are some of the most fascinating and mysterious objects in the universe. Supermassive black holes at the centers of galaxies power these incredibly bright and distant celestial bodies. Their intense energy output makes them visible across vast distances, allowing us to study the early universe and the formation of galaxies. Join us as we dive into the captivating world of quasars and uncover the secrets they hold. By 1960, radio astronomers had uncovered and compiled a fascinating array of hundreds of radio galaxies, with around 50 of these being recognized by optical astronomers as colossal elliptical galaxies. The mysterious radio galaxies appeared far too dim to capture on photographic plates. In 1960, a fascinating series of events unfolded, leading to the discovery of some truly enigmatic objects, quasi-stellar objects, or as we now call them, quasars. Get ready to dive into the mystery. Interestingly, the radio source 3C48 stands out with its star-like appearance rather than the nebulous look of a galaxy, and it's known for emitting intense ultraviolet radiation. Before long, other objects that looked just like it, including 3C273, started popping up everywhere. They were a fascinating anomaly in our galaxy, standing out from the typical stars by emitting powerful radio waves. In 1963, the world was shaken by some truly astonishing news. Martin Schmidt from the Mount Wilson Observatory made a groundbreaking discovery when he identified emission lines in the spectrum of 3C273 that were shifted by an astonishing 16% to longer wavelengths. To put it simply, this radio source had a redshift of 0.16, meaning it was moving away from us at roughly 16% of the speed of light. In our ever-expanding universe, we see that all those distant galaxies and cosmic wonders are moving away from us. This fascinating phenomenon causes the light from these distant objects to shift towards the red end of the spectrum, offering a captivating glimpse into the nature of our universe. Let's put a pin in this topic for now, but it's worth noting that a redshift of 0.16 means we're looking at a distance of about 3 billion light-years. Fascinating, right? 3C273 is an intriguing object that captivates the imagination. It's an extragalactic phenomenon, and its redshift is a fascinating result of the universe's expansion. Let's dive deeper into what that means. Many other radio sources were identified as star-like objects with significant redshifts, revealing that these stellar radio sources were distant beacons emitting vast amounts of energy. Alan Sandage made a groundbreaking discovery. He found that many star-like objects beyond our galaxy are radio quiet. Fascinating, right? Did you know that the biggest optical telescopes out there can spot tens of millions of quasars? It's mind-blowing. As we gaze into the vastness of space, we're not just peering into the unknown. We're traveling back billions of years into history. Let's take a journey back in time and discover how quasars were once incredibly abundant in the universe compared to today. Back when our solar system was coming together, there were so many of them that at least one was close enough for us to see without any fancy equipment, shining in the sky like a dazzling jewel. Way back in the early days of the universe, just after galaxies began to form, things were buzzing with activity. At that time, the universe was only a fraction of its current age, and quasars were everywhere, popping up millions of times more frequently than we see today. Quasars unleash energy at an astonishing rate, about 100 times more than all the stars combined in a massive galaxy. They waste energy at this pace for usually 1 billion years or even longer. Imagine a scenario where matter is annihilated and transformed into energy. Think about the equation that tells us energy equals mass times the speed of light squared. In this mind-blowing context, some quasars could devour the mass equivalent of over 100 million stars throughout their existence. How wild is that? Did you know that the light from certain quasars fluctuates in brightness? It's fascinating how these cosmic giants can change on timescales as short as just weeks or even days. Tune in as we explore the mysteries of the universe. Typically, a bright source of light can't dramatically alter its visible look in a time frame shorter than it takes for light to cross its dimensions. When an object suddenly ramps up its brightness, what we perceive is a delayed response. This happens because the light from the closest areas of the surface reaches us first, while the light from the farther sections takes a bit longer to arrive. It's a fascinating phenomenon that makes you think about how we experience light and time. So if we see the light changing in brightness over just one day, it means that a spherical source must have a radius that's less than one light day, making it smaller than our entire solar system. Picture this: a grand ballroom that symbolizes the vastness of our galaxy. In this immense space, a brilliant quasar is just a speck of dust drifting through the air. How mind-blowing is that? Quasars are incredible cosmic powerhouses, emitting intense radio, infrared, visible, and ultraviolet radiation, all while being remarkably compact by the vast standards of the universe. What exactly are they? Radio quasars share similarities with radio galaxies, featuring either extended or compact regions that emit radio waves. Radio astronomers are unable to distinguish between them. Moreover, optical astronomers face a challenge in distinguishing quasars from the dazzling cores of radio galaxies, as they both appear strikingly similar. Did you know that the nuclei of most giant elliptical galaxies might experience a quasar phase during their early evolution? It's fascinating to consider that many quasars also undergo an active radio-emitting phase at some point in their lives. Imagine giant spirals lighting up the cosmos. These are Cepheids galaxies. With their bright, active nuclei, they showcase some seriously intense activity, almost like miniature quasars. It's a wild ride through the universe. It's been years since we first uncovered the mystery of quasars. Yet so many questions still linger about how these incredible cosmic phenomena produce and radiate such staggering amounts of energy across a vast spectrum of wavelengths. Amid the buzz of their groundbreaking discovery, a flurry of theories emerged. Some suggested the dramatic annihilation of matter and antimatter, while others speculated about dense stellar systems where stars collide spectacularly. There were also ideas about frequent supernovas and even potential changes to the very laws of nature as we know them. It's widely accepted that the release of gravitational energy is what powers the radiation we observe. The process likely kicks off with a flurry of star formation in the nucleus, where many of these stars go through fascinating transformations, evolving into neutron stars and black holes. These compact bodies gather gas and unleash energy in an exciting process. When stars are more massive than our Sun, they face an incredible fate at the end of their life cycle. They collapse and transform into black holes. The laws of nature, as we see them, point us to this fascinating conclusion. Edwin Salpeter from Cornell University developed the most popular and widely accepted explanation for quasars. Quasars are fascinating cosmic phenomena, essentially supermassive black holes that pull in gas at incredible rates. We've expanded the theory to cover all those wildly energetic galactic nuclei. Think quasars, radio sources, Cepheids galaxies, and other intriguing similar objects, now collectively known as active galactic nuclei. It's a fascinating topic that gets the mind racing. Not all the gas that falls into a galaxy gets used up in star formation. Some of it sticks around, ending up in the beautiful disks of spiral galaxies or the dense nuclei of elliptical ones. Imagine a colossal elliptical galaxy where a massive influx of gas gathers at its core, potentially making up about 1/10 of the entire galaxy's mass. It's a fascinating cosmic phenomenon that sparks curiosity and wonder. The gradual contraction of this matter reservoir gives rise to a quasar that will dazzle us for the next billion years. In a massive spiral, the gas building up in the core is significantly reduced, leading to a decrease in nuclear activity. The journey begins with the formation of countless stars in a gas-rich nucleus, where many of these stars quickly evolve into black holes. Picture this: a black hole, a cosmic giant a few times the mass of our Sun, stretching across a diameter of roughly 10 kilometers. Now, please place it in a bustling nucleus, where gas is thick, and millions of stars are packed tightly together, creating an awe-inspiring celestial scene. The scene brings to mind those chilling words, "Cry havoc, and let slip the dogs of war." The shout, "Havoc," was a call to unleash chaos and destruction without mercy. During the time of Richard II in England, it was strictly prohibited to utter the cry, with the severe consequence of death for those who dared to do so. Picture this: gas swirling around a black hole, creating an incredible accretion disk where matter spirals in, drawn into the mysterious depths of the black hole. It's a cosmic dance that captivates the imagination. Stars that venture too close to a black hole face a dramatic fate. Either they collide with each other or get ripped apart by powerful tidal forces. The remnants of these gaseous giants contribute to the chaotic dance spiraling into the black hole. Next time you pull the plug out of a bath and watch the water swirl down in a mesmerizing dark vortex, imagine it as a ravenous black hole pulling everything in its path. Imagine a black hole that's on a cosmic feeding frenzy, rapidly increasing in mass and occasionally devouring smaller black holes in its path. It's a wild and fascinating phenomenon in the universe. If a galactic nucleus is packed with gas and stars, a black hole can balloon to a staggering 100 million times the mass of our Sun in just a few 100 million years, reaching an impressive size of 1 light hour. Fascinating, right? An incredible surge of energy bursts forth from the swirling, inflowing gas as it expands and evolves. Picture this: gas spiraling into a black hole, getting squished and heated to mind-blowing temperatures, then blasting away its energy in a spectacular display. It's a cosmic dance of destruction and transformation. The gas that's been captured transforms a portion, around 10% or even more, of its mass into radiant energy that escapes into the universe. Imagine a colossal black hole ballooning to a staggering billion solar masses while unleashing an incredible amount of energy, equivalent to at least 100 million solar masses. It's a cosmic phenomenon that truly captivates the imagination. This captivating image of a quasar showcases its incredible brilliance and diminutive size, shedding light on how it may have transformed into a powerful radio source. The sizzling, electrically charged gas spiraling into the black hole functions like a colossal dynamo, unleashing powerful beams of high-energy particles in opposite directions. It's a cosmic spectacle you won't want to miss. These particles venture out and supercharge the radio-emitting areas of radio sources. In this sweeping overview, we see that quasars are found at the heart of galaxies, shining brightly in their most dynamic phases. They only fade away once they've consumed or expelled most of the matter surrounding them. After that, the black hole goes quiet, only to burst into action now and then when new gas supplies arrive. In spiral galaxies, you'll find that the gas concentration in their nuclei is lower, and interestingly, the black holes present in these spirals are likely more minor compared to those in giant elliptical galaxies. Recent radio studies have revealed some fascinating insights about the nucleus of our galaxy. It turns out that black holes could be hiding in this central region, as well as in the cores of other massive spiral galaxies. These black holes might have mind-boggling masses, ranging from hundreds to thousands. Did you know that from our very own Earth, you can spot around 2,000 stars just with your naked eye? It's a stunning reminder of the vast universe above us. When you have a quality pair of binoculars, that number jumps to an impressive 12,000. Did you know that our galaxy is home to roughly 100 billion stars? And if you look beyond that, the visible universe boasts an astonishing 10 to the power of 20 stars. It's mind-blowing to think about the sheer number of celestial bodies out there. The closest star system to us, Alpha Centauri, is made up of 2 stars that are so close together that you can't see them separately without a telescope. Fascinating, right? Imagine a fascinating triple star system where a faint, intriguing third star, Proxima Centauri, hangs just a bit closer to us. It's a cosmic dance that sparks curiosity and wonder. Sirius, known as the brightest star in our night sky, besides the Sun, is accompanied by a subtle white dwarf companion that adds to its intriguing story. Since the days of Hipparchus in the 2nd century BC, astronomers have been using a fascinating system known as magnitudes to gauge the brightness of stars. It's a captivating journey through time and space that connects us to the cosmos. Stars that we can see are grouped into 6 different magnitudes. The first magnitude includes the brightest stars we observe, while the 6th magnitude features the faintest ones that still catch our eye. In 1836, John Herschel made a groundbreaking discovery. Stars classified as 1st magnitude shine 100 times brighter than those in the 6th magnitude. Fast forward to 1850. And astronomer George Pogson revealed that each step up in magnitude means a drop in brightness by a factor of 2.5. Fascinating, right? Check this out. When we look at the relation 2 to 5555100, it reveals some fascinating results. Specifically, an increase of 5 magnitudes from the first to the sixth means there's a staggering 100-fold decrease in brightness. Isn't that mind-blowing? Did you know that a star of second magnitude is actually 2.5 times fainter than a star of first magnitude? And here's a fun fact. A star with a magnitude of m is 2.5 raised to the power of m minus 1 times fainter than a first magnitude star. Isn't that fascinating? Astronomers stick to some unusual units like parsecs and magnitudes, all thanks to tradition, much to the frustration of their fellow scientists, especially those in the physics realm. They steer clear of the trendier units. Interestingly, while most scientists stick to meters and kilograms, astronomers have their unique approach. They prefer centimeters and grams, thinking that when it comes to the vastness of space, the difference between these units is just a drop in the cosmic bucket. What are the advantages of transitioning from one system of units to another, especially when both incorporate complex numbers? Astronomers often cling to traditional units or opt for newly created ones, which can complicate matters when dealing with astronomical quantities. When we talk about distances in space, we often use astronomical units, parsecs, or light years. For masses, we refer to them in terms of xm8, which means x times the mass of our Sun. And when it comes to luminosities, we express them as yl8, indicating y times the luminosity of the Sun. It's a fascinating way to understand the vastness of the universe. Did you know that matter in bulk comes in 4 fascinating states? That's right. We have solids, liquids, gases, and even plasma. Let's dive into each one and explore their unique characteristics. Solids are fascinating structures. They're rigid and held together by powerful interatomic electrical forces, with atoms that vibrate around fixed points. Let's dive deeper into the science behind these incredible materials. Liquids, gases, and plasmas are fascinating types of fluids where atoms can move freely, showing less influence from the forces that usually keep them in check. As the temperature of a solid increases, the atoms start to vibrate more intensely. And whether individually or in groups, they begin to move around each other. The solid has transformed into a liquid. When temperatures rise, the atoms start to vibrate intensely, breaking their bonds and transforming into a gas filled with freely moving particles. It's a fascinating process that showcases the dynamic nature of matter. When temperatures soar beyond a few thousand kelvins, something fascinating happens. The atoms get ionized, transforming the gas into a plasma filled with free electrons and atoms that are either partially or fully ionized. It's a wild state of matter that showcases the incredible dynamics of the universe. Did you know that the majority of matter in the universe exists in the plasma state? It's a fascinating concept that opens up a whole new realm of understanding about our cosmos. Imagine a world where we harness the power of the stars right here on Earth. The ultimate goal of cutting-edge science is to unlock the secrets of nuclear fusion, just like the Sun does. This could revolutionize our energy landscape. We're diving into an exciting concept here. Imagine harnessing deuterium, that abundant heavy hydrogen found in our oceans, as a game changer. This could help us sidestep the pesky, slow, and weak interactions that often slow down the proton-proton chain. It's a fascinating twist in the world of nuclear fusion. However, the initial challenge, the electrical repulsion between protons, persists, even though deuterons are eager to react when they come together, unleashing a burst of nuclear energy. The challenge of overcoming their electrical repulsion barriers remains a significant hurdle. Many people think that the secret to achieving fusion lies in mimicking the stars themselves. So, we need to crank up the heat on the deuterium gas to a staggering tens, even hundreds of millions of Kelvin. The hydrogen bomb, utilizing a fission bomb as its trigger, has already unleashed an uncontrolled release of thermonuclear energy. If the Sun were made up entirely of heavy hydrogen, it would also face an explosive fate. We're on the brink of something incredible with fusion energy, but there's a big challenge ahead. The quest to keep that gas contained at such extreme temperatures for a prolonged period remains an unsolved puzzle. Let's dive into this fascinating topic and explore what following permanently established laws. William Thomson, on the age of the Sun's heat. This thought-provoking statement invites us to ponder the origins of our Sun's energy and the mysteries of the universe. Building on a fascinating concept from the German scientist Hermann von Helmholtz, he suggested that the Sun replenishes its emitted energy through a gradual process of gravitational contraction. He discovered that the age of the Sun, using this method now referred to as the Helmholtz-Kelvin time scale, is roughly 20 million years old. Before we unlocked the secrets of nuclear energy, the idea of gravitational contraction was widely seen as the most logical and straightforward explanation for how the Sun and stars shine so brightly. Imagine a Sun that's just 20 million years old. While that might seem like a lot compared to what some ancient texts suggest, it's way too brief for the vast timeline of geological history and the incredible journey of biological evolution. This sparked serious debates among physicists, geologists, biologists, and paleontologists, especially as the late 19th century drew near. The discussions were heated and fascinating as experts from different fields clashed over the actual age of our planet and the life it harbors. The groundbreaking discovery of radioactivity, along with the stunning revelation that our solar system is billions of years old, finally settled the debate once and for all. The Helmholtz-Kelvin timescale plays a crucial role in understanding stellar structure theory. Let's dive into the fascinating world of radiant energy and explore its heat content on this timescale. During the 20th century, scientists made some incredible observations of supernovas happening across different galaxies. For a brief period, each supernova can shine brighter than all the stars in its entire galaxy, captivating our imagination and illuminating the cosmos. Over the past 2 millennia, we've documented 14 supernovas in our galaxy, with the most recent sighting occurring in 1604. One of the most famous supernovas in history, the one that lit up the sky in 1054 in the constellation Taurus, was documented by the Chinese. Today, its remnant is known as the stunning Crab Nebula. Did you know that Tycho's star, which lit up the night sky in 1572, was located in the constellation Cassiopeia? And just a few decades later, in 1604, Kepler's star made its appearance in the constellation Serpens. Fascinating stuff, right? Back in 1572, Tycho Brahe had a moment that would leave anyone in awe. He wrote about one evening when he was gazing at the familiar night sky, and suddenly, near the zenith in Cassiopeia, he spotted a brilliant star that was unlike anything he had ever seen before. Can you imagine the excitement of that discovery? Historically, cosmology has focused on the center and the edge of the universe, with our understanding of location and containment reflecting our present-day perspective on these intriguing concepts. Let's dive into the fascinating world of cosmic principles. First up, we have the location principle, which tackles the mysteries of the cosmic center. Then we shift our focus to the containment principle, exploring the intriguing concept of the cosmic edge. Stay tuned as we unravel these cosmic concepts together. These principles guide us in steering clear of the traps that previous cosmologists encountered. Imagine a principle that defines the very essence of our physical universe. It's all-encompassing, holding everything physical within its bounds and leaving nothing outside of it. Intriguing, right? This principle stands as the cornerstone of the physical sciences, particularly in the realms of chemistry and physics. For some, this principle seems so basic and clear that it barely warrants a mention. Yet for others it represents a bold and controversial philosophy. Before we rush to dismiss this principle as overly simplistic or ridiculous, let's take a moment to dive deeper into its true meaning. Modern scientific cosmology explores a physical universe that encompasses everything tangible while excluding non-physical aspects. Physicality is a fascinating concept that extends far beyond what we typically consider appropriate. It's a term that invites exploration and challenges our everyday understanding of the world. It includes all measurable elements linked by ideas that can be challenged. Atoms and galaxies, cells and stars, organisms and planets. These are the incredible physical entities that make up our fascinating universe. Let's dive into the fascinating world of physics. We're talking about particles and their incredible duality, the mesmerizing dance of atoms and electron waves, and the intricate coding of DNA. We'll explore the fields and waves that ripple through the cosmos, the captivating virtual realms of the vacuum, and the mind-bending concepts of special and general relativity. Plus, we'll take a journey through the vastness of the astronomical universe. Buckle up for an exciting exploration of the physics. But wait, there's even more to uncover. As beings with bodies and minds, we find ourselves navigating the confines of the physical universe. Space and time aren't merely empty canvases where the universe exists. If they were, we could see spots in the cosmos and timeline that the universe hasn't filled. Let's dive into this fascinating concept together. Space-time isn't just a simple container. It's a dynamic, four-dimensional continuum that intertwines space and time in a genuinely fascinating way. It's a fascinating continuum that holds a unique reality of its own. Space and time are dynamic players in the grand design of the universe. They are integral to the physical realm and don't reach beyond its boundaries. The universe is a fascinating concept that encompasses both space and time. But intriguingly, it exists beyond the limits of space and time themselves. If you subscribe to the idea of a non-physical realm like heaven, then you have to consider how it fits into our concepts of space and time. We can't stretch our understanding of space and time to encompass heaven because doing so would pull heaven into the physical universe, subjecting its existence to the scrutiny of scientific investigation. Dynamic properties reveal the fascinating physical essence of space, or more accurately, space-time. Vast, empty regions of space interact and have an impact on each other in fascinating ways. This process captures the very heart of general relativity. Let's dive into the fascinating world of gravity. In countless past universes, space and time served as the grand stages for the epic cosmic drama to unfold. In today's dynamic physical universe, space and time take center stage as the leading players. It's hard to question the tangible nature of space, or space-time, when you consider its incredible influence. It shapes the tides, orchestrates the moon's dance around our planet, and keeps Earth in its orbit around the sun. And let's not forget the dramatic consequences for astronauts and their ships if they venture too close to neutron stars and black holes. The universe is a wild place, and its physical laws are nothing short of awe-inspiring. Space might be limited, but it has no boundaries. Imagine the smooth, curved surface of a sphere. It's a perfect analogy that's easy to picture and understand. The surface is finite, yet it has no edge. An intriguing concept that invites us to explore the mysteries of dimensions and boundaries. Imagine an ant making its way in a straight line across the surface of a spherical watermelon, only to find itself back where it began, all without ever hitting an edge. How fascinating is that? The cosmic journey circles back to where it all began. Some argue that the containment principle overlooks everything that truly matters. Let's dive into the fascinating realms of our souls, minds, and consciousness. What about all the incredible depth and richness of our inner mental world? It's a topic that sparks curiosity and invites exploration. How do they fit into the bigger picture? The answer is crystal clear. They aren't found anywhere. At most, only their physical counterparts, like chemical activities, really cut. The wonders of life can be boiled down to the fascinating biochemistry of our brain's neurons. When addressing those who seek a tidy explanation of the spiritual, psychological, and physical aspects of the universe, we need to clarify. You're mixing up the universe with the universe. The unknown universe encompasses everything, including our thoughts and consciousness, while the known physical universe is limited to what we can observe, including our brains. Hey there, listeners. Let's dive into the fascinating world crafted by mathematicians, physicists, biophysicists, and chemists. They've shaped our incredible universe, and if it doesn't resonate with you, well, it's time to create your version of reality. How exciting is that? Modern cosmology dives deep into a physical universe model, presenting the universe as a captivating veil that shrouds the unknown. And what an incredible mask it is. The brilliance of history's greatest scientific minds has shaped it. Yet, when faced with the grandeur of this physical universe, I can't help but ponder why so many, even scientists, confuse this latest mask with the true essence of the universe's mysteries. In the fascinating realm of the ancient Mediterranean, we find the atomists and Epicureans boldly advocating for a limitless, centerless, and boundary-free universe. On the flip side, the Aristotelians and Stoics stood firm in their belief in a finite cosmos with a distinct center and edge. Central to this captivating debate was the intriguing question of the cosmic edge itself. In the 4th century BC, Epicurus shared a fascinating insight. Democritus of Abdera claimed that the universe has no end. Any outside force didn't create. He went on to explain that the concept of boundaries is intriguing, as anything limited must have an extreme point, which can only be understood about something else. What a thought-provoking idea. In the 1st century BC, Lucretius the Epicurean, inspired by the intriguing riddle of Archytas, crafted his stunning poem De Rerum Natura. He mused, "It's clear that one thing defines another. The air outlines the hills, and the hills outline the air. The land sets limits to the seas, and the seas to every land. Yet, there's nothing beyond imposing limits." He challenged those who believed in a confined universe. Imagine for a moment that all of space is bounded, and someone reaches its farthest edge and throws a dart. Do you think that the dart, launched with all its force, would follow its intended path? Or would something obstruct it? You have to consider one of these possibilities. With this thought, I'll keep pushing you. So, what happens to the dart? Regardless of where you draw the line, Lucretius responded to the atomist, "Understand this. The universe knows no boundaries in any direction." In the 6th century AD, Simplicius left a memorable quote that still resonates today. In his insightful commentary on Aristotelian physics, Archytas poses a thought-provoking question. If I find myself at the very edge of the heavens, among the fixed stars, can I extend my hand or staff outward? It's downright ridiculous to think that I couldn't. If I can, then what lies beyond must either be a physical entity or some space. And just like that, we can step back outside and keep the momentum going. When there's always a fresh destination for the staff to reach, it signifies an endless expansion ahead. In the captivating dialogue of the infinite universe, penned by Bruno during his time in England, we encounter a fascinating exchange between Berkio, an imagined Aristotelian, and Philotheo, who embodies Bruno himself. Berkio presents a thought-provoking argument. If someone were to stretch their hand beyond the convex sphere of heaven, it would occupy no position in space, and thus it wouldn't exist at all. Philo counters this by asserting that space, whether inside or outside the universe, is continuous and identical. He provocatively asks, what lies beyond? If the answer is nothing, then we are left with the concept of void or emptiness. This dialogue invites us to ponder the very nature of existence and the mysteries that lie beyond our understanding. Imagine a void so vast and limitless, yet it still has a boundary. It's a fascinating concept that invites us to explore the depths of emptiness and what it truly means. This emptiness is more complex to imagine than an infinite or immense universe. This intriguing commentary by Simplicius, a Neoplatonist, remained under the radar until it was translated into Latin in the 16th century. Meanwhile, the influential poem by Lucretius, rediscovered in 1417 in a monastery, gained significant traction, especially among scholars such as Nicholas of Cusa, Giordano Bruno, Thomas Digges, and William Gilbert, who were captivated by its profound insights. In a finite universe, everything was connected to a clear cosmic center and edge, shaping the way we understood the cosmos before Copernicus. However, as astronomical discoveries unfolded, the idea of a cosmic center was dismantled, and the mystery posed by Archytas challenged the very notion of a cosmic edge. Imagine diving into the concept of an infinite universe, a notion that might have surfaced as a response to the cosmic edge riddle, whether through Archytas's perspective, or perhaps even in some earlier, unrecorded way. The atomists and Epicureans, however, were completely unfazed by this riddle. They embraced the idea of infinite space, teeming with stars and planetary systems, alive with possibilities at the very edge of the universe. As we explore further, we'll uncover how tackling the cosmic edge riddle in this manner sparked the intriguing mystery of the night sky. Imagine a time when ancient thinkers believed the universe had a definitive end marked by a colossal wall. In the realm of mythology, this vast cosmos was often visualized as encased in a shell or a cavern with dark, imposing walls. Fast forward to the Aristotelian era, where the edge transformed into a sphere of fixed stars. Even the brilliant Johannes Kepler joined the conversation, proposing that the universe was surrounded by a mysterious cosmic fence, which helped him tackle the intriguing question of why the night sky remains dark. He boldly claimed that in a universe teeming with stars, the night should be ablaze with light. But did Kepler truly crack the code of the cosmic edge mystery? If there is indeed a wall-like boundary, what happens next? Does it bounce back, or does it allow passage? Epicurean skeptics weigh in, arguing that a boundary cannot be both limiting and limitless, while the alternative implies that perhaps the edge is merely an illusion. Dive into this cosmic conundrum with us. In the later iterations of the Aristotelian universe, particularly during the Neoplatonic and medieval periods, the concept of space didn't just stop abruptly. Instead, it faded away gradually, starting from the lunar sphere. As you journey outward from Earth, the physical world seamlessly transitions into an etheric realm. In the medieval interpretation, this outer etheric celestial realm is enveloped by the Empyrean, a divine space inhabited by God. This leads us to ponder. What truly happens to a physical body as it ventures away from Earth? The elements of our physical bodies either stay the same and return to the Earth, much like a stone thrown into the air that eventually falls back down, or they transform into ethereal elements. In this case, their natural movement becomes circular around the Earth instead of just going up and down. The medieval universe had a striking boundary, and the power of, with argument, I shall pursue you, diminished as the pursuer ventured into an ethereal outer realm, where physical arguments lost their impact. This cosmic edge resembled a slow transition from solid ground to a shaky marshland. The medieval response to this riddle is no longer valid. Current observations show that the physical world does not simply dissolve into a non-physical realm at vast distances. Exploring the Stoic cosmic edge, imagine a universe where a finite cosmos of dazzling stars meets an infinite, starless void. Picture the Stoic edge, sharp and dramatic like a cliff, creating a stark division between a vibrant inner cosmos and the endless expanse of outer space. The cosmic edge riddle has a straightforward answer. By throwing a spear, you can expand the cosmos and push its boundaries further out. In the early days of Stoic thought, this infinite void was a fascinating addition to the traditional Aristotelian sphere of stars, likely inspired by the intriguing riddle posed by Archytas. Join us as we dive deeper into these captivating ideas and explore the mysteries of the universe together. Picture this. The medieval universe transformed into a grand Stoic cosmos filled with stars, where the infinite void became the divine realm of God. This captivating cosmic vision captured the imagination of many. It was the perspective of Isaac Newton during his early years at Cambridge, the Milky Way cosmos envisioned by William Herschel in the late 1700s, and the Victorian universe that thrived well into the early 20th century. Imagine, if you will, traveling beyond the Milky Way in your mind, gazing back to witness a breathtaking view of the entire material universe. Observations have shown that this vast universe stretches far beyond the Milky Way with no signs of a definitive edge. What an awe-inspiring thought. Exploring the universe from a fresh perspective. When diving into the fascinating world of cosmology, many people picture the universe as a spherical cloud of galaxies, expanding in space with a defined center and edge. However, this common image is misleading and contradicts the fundamental principles of containment. Space isn't just an empty container for the universe. It's a physical entity that expands alongside it. Space is an integral part of the universe itself and cannot extend beyond its boundaries. Contrary to the Stoic perspective, the Big Bang didn't happen in a specific location within space. It encompassed all of space. If we consider space to be infinite, then the Big Bang was also endless. An infinite universe remains perpetually infinite and cannot transition into a finite state. No matter where we are now, we must remain still and travel back in time to truly understand our existence during the moment of the Big Bang. Picture this: an infinite three-dimensional space that has no center and no edges. It's a concept that's not too hard to wrap your mind around. But what about a finite version of that? Now that's where it gets tricky. Instead, let's shift our focus to something a bit more tangible. A two-dimensional surface that is both finite and lacks a center or edges. Think of a spherical surface. It's limited in size yet beautifully seamless, with no defined center or edge to constrain it. Imagine a universe without boundaries. Unlike Dante and Beatrice's epic journey in the Divine Comedy, we can't simply travel to the edge of space for a breathtaking view. Instead, picture this. In our ever-expanding universe, galaxies aren't racing away from us. They're staying put while the very fabric of space stretches, much like the surface of a balloon as it's inflated. Stick around because we'll dive deeper into how this cosmic expansion pulls galaxies further apart. Just like space, time is a tangible part of our universe, but it also reaches beyond it, touching on a cosmic edge that's all about the flow of time. Instead of pondering what the universe might be like before or after time runs out, we should steer clear of those questions, much like we wouldn't ask what lies beyond the boundaries of space. These kinds of inquiries challenge the very idea that the physical universe encompasses all that is physical. Cosmogony, which refers to the creation of cosmic progeny, delves deep into the fascinating origins of astronomical structures, such as planets, stars, and galaxies. It even touches on the beginnings of elements and life itself. The fundamental constraints of cosmogony are pretty simple. Everything must fit within the size of the universe. Let's explore a captivating sequence of events in this cosmic journey. Nuclear chronology delves into the fascinating world of how elements are formed and their history through various dating techniques. Imagine the early universe, a hot and dense place where light elements like deuterium and helium were born from protons and neutrons during the Big Bang. Fast forward to the life of stars, which created most of the other chemical elements and blasted them into space during spectacular supernova explosions. Before our solar system even existed, these stars laid the groundwork for the elements that make up our Earth. Many of these heavy elements are radioactive, slowly transforming into daughter elements over time. Take uranium-235, for instance. With a staggering half-life of 4.5 billion years as it decays into lead. By studying the decay rates of these radioactive elements and their current abundances, scientists can unlock the ages of the Earth, the solar system, and even our galaxy. The results are mind-blowing. Our solar system is about 4.6 billion years old, while the galaxy itself is around 13.8 billion years old. Cosmologists have some fascinating insights into the age of our universe, estimating its expansion rate to be between 10 and 20 billion years old. But here's the twist. Back in the late 1920s to the mid-1950s, they thought the universe was just over 1 billion years old. Imagine that. A universe younger than Earth. This age paradox created quite a stir in the world of cosmology for about 25 years. Researchers got creative, trying to find ways around this conundrum, leading to concepts such as the hesitation universe, where expansion was extremely slow for a long stretch, and the steady-state theory, which suggested an infinite past. It's a captivating journey through the mysteries of our cosmos. Georges Lemaitre and George Gamow, two trailblazing cosmologists who championed the Big Bang theory, initially believed that this monumental event was responsible for creating most of the elements we see today. While this notion was later proven incorrect, it ignited a spark of curiosity in Gamow and his team, Ralph Alpher and Robert Herman, who boldly ventured into the concept of a hot early universe. Their groundbreaking work led to the prediction of cosmic background radiation, nearly 2 decades before it was discovered. On the flip side, the steady-state theory, although ultimately flawed, had its merit. Its proponents rejected the idea of Big Bang nucleosynthesis, compelling them to demonstrate that all heavy elements are forged in the hearts of stars. The visionaries behind the successful theory of stellar nucleosynthesis included Alastair Cameron, Margaret and Geoffrey Burbidge, William Fowler, and Fred Hoyle, who paved the way for our understanding of the cosmos. In the 1950s, Walter Baade and Alan Sandage, along with others, revised our understanding of extragalactic distances, leading to a significant increase in the estimated size and age of the universe. This fascinating development suggests that we can fit the ages of chemical elements, the Earth, the solar system, stars and galaxies, into the timeline of a Big Bang-type universe. It's a captivating topic that sparks discussions about the cosmos and our place within it. Have you ever wondered why our universe mirrors the existence of life in so many fascinating ways? Throughout history, we've seen mythology and theology champion the idea of a universe crafted with intention. The notion that our universe was purposefully designed to be a perfect home for humanity is a concept that dates back to ancient creation myths. Let's dive into this intriguing topic together. The design argument suggests that the presence of a supreme designer is evident in the intricate cosmic design and the marvels of nature all around us. This argument took on a fresh and clear shape in the 18th century, particularly with the rise of deism, influenced by the groundbreaking ideas of the Cartesian and Newtonian perspectives. Theism is the ancient belief that a supreme being creates and runs the universe. The universe is the new belief that a supreme being creates a universe so perfect in design that supernatural maintenance is unnecessary. In 1687, Thomas Burnet, a clergyman, wrote in Theory of the Earth, "We think him a better artist who makes a clock that regularly strikes every hour from the springs and wheels he puts in the work, than he who hath so made his clock, that he must put his finger in it every hour to make it strike." 18th century deists often employed the clock analogy to support the design argument. In 1702, Archdeacon William Paley, in his book Natural Theology, argued that the complex designs of the eye and hand could not have happened by chance through nature alone. He wrote, "I found a watch on the heath, and it follows that the watch must have a maker, that there must have existed at some time and at some place or other an artificer or artificers who formed it for the common purpose, which we find it actually to answer, who completely comprehended its construction and designed its use." But in the years ahead, the advance of science made it increasingly apparent that the forces of nature are not so blind as Paley believed. In the fascinating Bridgewater Treatise, crafted by 8 distinguished authors to highlight the power, wisdom, and goodness of God as manifest in the creation, chemist William Prout made a remarkable observation back in 1834. He pointed out the intriguing behavior of water as it expands when it freezes, showcasing a stunning example of nature's design. It's almost as if this phenomenon was intentionally orchestrated to serve a specific purpose. Prout emphasized that if water didn't expand upon freezing and ice remained solid, our oceans would be locked in ice, rendering life on Earth utterly impossible. What a thought-provoking insight into the delicate balance of our natural world. Science has unveiled a breathtakingly intricate world driven by powerful forces that shape our existence. Take natural selection, for instance. It's the key to understanding how the remarkable features of our eyes and hands evolved. But the wonders of the physical realm go beyond just these structures. They dive deep into the atomic and subatomic levels, creating a universe that is perfectly tailored for life. Join us as we explore these incredible phenomena that make our world so extraordinary. In 1913, Lawrence Henderson, a renowned scientist from Harvard University, made a fascinating observation in his work, The Fitness of the Environment. He pointed out that the environment's fitness stems from a series of unique properties. Think water, carbonic acid, and the essential compounds of carbon, hydrogen, and oxygen. These elements come together in such a remarkable way that they create what he described as the greatest possible fitness. Fast forward to today, and developments in physics reveal that this molecular fitness is rooted in fundamental design at the atomic and subatomic levels. It's a captivating intersection of science that continues to intrigue us. Exploring the concept of multiple physical universes. We've talked about universes, each one a unique model of the universe, showcasing not just one, but a multitude of physical universes, all self-contained and isolated from one another. Imagine a mind-bending scenario where the fundamental constants of nature vary from one universe to another. We're talking about those essential yet mysterious elements like the speed of light, the gravitational constant, and the electric charge of protons and electrons. Picture an incredible collection of universes, each with its own unique set of these constants, creating a cosmic playground for exploration. In some of these realms, gravity is a heavyweight champion, while in others, it barely makes a dent. And then there are those truly wild universes where quantum mechanics takes center stage on a grand scale, or is so minuscule that it hardly makes a splash. Join us as we dive into this fascinating cosmic menagerie and uncover the astonishing possibilities that lie within these alternate realities. Did you know that even the most minor tweaks to the fundamental constants can lead to massive shifts in the cosmic landscape? Just a slight variation in the values of C, H, and E can dramatically alter the very structure of atoms and their nuclei. Stable atomic nuclei are a rarity across the multiverse, with many universes consisting solely of hydrogen gas and missing out on crucial elements like carbon, nitrogen, and oxygen that are vital for organic life. It's a mind-boggling thought, though. Minor tweaks in the values of constants like C, G, H, E, and the masses of subatomic particles can lead to dramatic shifts in how stars are structured and evolve. Interestingly, in nearly all universes, stars are absent. In the few that do have them, most are either dim or so bright that their lifespans are far too brief for any form of biological evolution to take place. Imagine a universe where life as we know it could thrive. Our existence hinges on a delicate balance of chemical elements and the right environments. Think hospitable planets warmed by long-lived stars. A fascinating study reveals that only universes resembling ours meet these criteria. If the constants of nature were even slightly different, we wouldn't be here at all. Aristotle referred to these as the accidentals of nature, and they are finely tuned at a fundamental level. Most other universes with their unique designs are devoid of stars and life. It turns out our universe might be the rare gem in the cosmic ensemble that supports life. So let's dive into the incredible implications of how the laws of physics shape our very existence. Have you ever wondered why the constants of physics are so perfectly balanced? Is this fine-tuning a result of some grand design, or just a lucky coincidence? Or could there be an undiscovered theory out there that ties it all together and reveals why these constants have the specific values we observe? Let's dive into this intriguing mystery. Let's dive into the fascinating concept of the anthropic principle. This intriguing idea explores the relationship between the universe and our existence within it. It's a thought-provoking topic that raises questions about why the universe is the way it is, and how it relates to our very existence. Join us as we unpack this mind-bending principle and its implications for our understanding of reality. The universe is truly one of a kind, because we are here to witness it. This fascinating idea, known as the anthropic principle, was first articulated in a scientific context by Robert Dicke in 1961, and later expanded upon by Brandon Carter, with many others contributing to this captivating topic. In Shakespeare's Twelfth Night, the clown only shares part of the truth when he says, "That's what it is." The whole truth is even more profound. I exist as I am. Therefore, what exists, exists. Let's explore this mind-bending concept together. In 1974, Brandon Carter brought us the intriguing concept known as the anthropic principle. He laid it out. What we can observe is limited by the conditions that allow us to be here as observers. This idea, which he called the weak anthropic principle, is pretty straightforward. But then there's the strong anthropic principle, which dives into more controversial territory. It suggests that the universe is tailored for life. Life that has existed at some point in its vast history. This stronger version raises a whole host of philosophical questions that we often find ourselves navigating through. Have you ever found yourself pondering the mysteries of the universe? Questions like, why is the universe the way it is? Or why do atoms even exist? Can get the mind racing. Let's dive into these deep existential inquiries together. There are three possible responses. The first one is a functional question like, how do atoms work? Replaces the original question. In the realm of science, functional questions often take the place of existential ones. The second response dives into the theistic principle, suggesting that God is the mastermind behind cosmic design, ensuring everything aligns with life. However, this theological perspective puts a halt to scientific exploration. It raises intriguing counter-arguments like the question, why did God create the world in this manner? Who created and designed God? By asserting that the essence of God transcends human understanding. Let's dive into the fascinating concept of the anthropic principle. It suggests that the universe is precisely shaped for us to exist. Imagine that our very presence influences the cosmic design. If things were different, we wouldn't be here. In a multiverse scenario, different universes might play around with nature's quirks, giving us random outcomes. So why is our universe the way it is? It's all tied to our existence. But then, the big question arises, why do we exist in the first place? This brings us to the inherent nature of the universe itself. However, when we introduce theistic views, we complicate the argument by adding a supreme being, while the anthropic principle opens up the idea of multiple universes. Human existence doesn't restrict either principle. Every other creature on Earth is a reflection of a finely tuned universe. Wildflowers aren't found in separate universes. When you receive a wildflower, you're also receiving a glimpse of our universe's essence. Intelligent beings impose no more limitations on the universe than wildflowers do. The fundamental constants of our universe present a fascinating puzzle. Are they the result of intentional design, or are they simply a happy accident? While some might lean towards the theistic principle or the anthropic principle, the truth is that science thrives on unraveling the mysteries of what we once deemed inexplicable. Who knows? In the future, we might uncover a logical framework that gives these constants meaning beyond mere chance or intention. Stay tuned as we explore the depths of this intriguing topic. We often lean towards anthropic or theistic concepts, sidestepping the broader discussion to focus on practical matters. We have two intriguing ideas. Either our universe is just one of many existing because of our presence, or it's naturally designed, which puts a cap on further scientific exploration. When faced with the option of a supreme being that transcends rational understanding versus a desolate expanse of mostly dark and empty universes, it's no surprise that many would opt for the former. The laws of nature are like the ultimate guidebook that helps us make sense of the harmony and order in the universe. They uncover the fundamental patterns of space-time, showing us how it unfolds into three-dimensional space and one-dimensional time. Often, these laws are expressed through mathematical frameworks that reflect the world as we perceive it. We cling to these concepts until they clash with our observations, prompting us to adapt or even reconsider them. It's fascinating to think that the laws we understand today were once different and will likely evolve in the future. Science is an incredible journey that takes us from the tiniest atoms to the vastness of galaxies. Just imagine atoms are about 10 to the power of -8 centimeters, while galaxies stretch out to an astonishing 10 to the power of 23 centimeters, which is around 100,000 light years. That means galaxies are a mind-blowing 10 to the 31st power, times larger than atoms. This fascinating range of sizes spans an impressive 31 orders of magnitude, showcasing the incredible diversity of our universe. In the fascinating world of science, most of the phenomena we explore exist in that intriguing middle realm of physics. At the atomic level, electromagnetic forces explain nearly everything. While at the galactic scale, it's all about gravitational forces. When we shift our focus 5 orders of magnitude up to a cosmic size of 10 to the power of 28 centimeters, that's a staggering 10 billion light years. and down 5 orders of magnitude to a subatomic size of 10 to the minus 13 centimeters, the size of a nucleon, we step outside the familiar middle realm and dive into the less charted outer realms of physics. Buckle up, because this journey is anything but ordinary. In the vast expanse of the cosmos, gravity reigns supreme, shaping the very fabric of our universe through the dynamic curves of space-time. Yet, as we dive into the subatomic world, we encounter a fascinating interplay of forces, both weak and strong, alongside electromagnetism. This creates a striking contrast. The universe appears simple on a grand scale, while complexity thrives at the atomic level. Interestingly, the electromagnetic and weak forces are like two sides of the same coin, known as the electroweak force, which were once unified in the high-energy conditions of the early universe. Even more intriguing, these forces are part of a hyper-weak force that existed at even greater energies in the universe's infancy. While the differences between the atomic and cosmic realms may seem pronounced, they are not entirely distinct. After all, the universe is built from atomic particles, reflecting a complexity that mirrors the very nature of those particles themselves, exploring the principles of internal and external relations. The university is still on the quest to uncover the physical properties that connect particles to the vast cosmos. This intriguing concept is rooted in the age-old principle of bootstrapping. The bootstrap principle suggests that everything is interconnected, with each element containing a piece of the whole. Anaxagoras famously noted, "In everything there is a portion of everything." Physicist Geoffrey Chew echoed this sentiment, stating, "Nature is as it is because its entirety is the only possible nature consistent with itself." This concept highlights that the dynamics of the universe at the largest scales influence the most minor details, and vice versa. Gottfried Leibniz's theory emphasizes that the macrocosm mirrors the microcosm. This intriguing idea resonates with Victor Hugo's thought, "Where the telescope ends, the microscope begins." So, which perspective offers the grander view? It's fascinating to think that, at a fundamental level, both perspectives might be on the same wavelength. Back in the 18th century, Bishop Berkeley introduced the bootstrap principle, suggesting that the distribution and masses of all other bodies in the universe shape its inertia. Fast forward to the 19th century, and we see the universe presenting a similar concept. This bootstrap argument, which we now call Mach's principle, went on to inspire none other than Albert Einstein. Alfred Whitehead, a notable philosopher, introduced us to the intriguing concept known as the doctrine of external relations. Imagine everything in our universe operating in a dynamic push-pull dance, shedding light on our shared human experience of navigating a competitive landscape. Now, when we dive into existential questions, like why all electrons share the same electric charge, we find ourselves in a bit of a puzzle within the atomist worldview, where these questions often get brushed aside. Yet this atomist perspective does offer some practical insights into how objects move around us. Join us as we unravel these fascinating ideas and explore their implications for our understanding of the universe. We see signs of internal relations emerging in physics. Newtonian gravity was an external relation of the push-pull kind. General relativity is a much subtler scheme of things. Gravity, as we know it, vanishes, and is replaced by the dynamic curvature of space-time exhibiting properties of internal relationships. However, despite our tendency towards abstraction, we still refer to gravity as a force despite its disappearance. Quantum mechanics uncovers a strange world of internal relations. As Richard Feynman said, "Nobody understands quantum mechanics. An excited atom in the depths of space decays and, while decaying, emits a photon wave in all directions. A million years later, a million light-years away, the wave enters a telescope on Earth and creates an electrical signal in a detection instrument. Instantly, the entire spherical wave throughout space collapses into the photon, emitted by the decaying atom, and received at the detector. The photon can be watched only once. Therefore, the entire wave, spread out over millions of light-years, collapses at the moment of observation of the photon. In the push-pull world of external relationships, a world invented long ago by primitive humans, such behavior is mysterious. The old atomist principle tells us how but not always why. The implicate principle tells us why but not always how. Perhaps, in a hypothetical world of intelligent and non-aggressive creatures, the doctrine of internal relations fully explains everything. Did you know that if you look up at the night sky, you can spot around 2,000 stars with just your eyes? It's a fascinating glimpse into the vast universe above us. When you have a quality pair of binoculars, that number skyrockets to an impressive 12,000. Did you know that our galaxy is home to roughly 100 billion stars? And when you look beyond that, the visible universe boasts an astonishing 10 to the power of 20 stars. It's mind-blowing to think about the sheer scale of it all. Did you know that the closest star system to us, Alpha Centauri, is actually made up of two stars that are so close together you can't see them separately without a telescope? Fascinating, right? Imagine a fascinating triple star system. In this cosmic dance, we have a third star, Proxima Centauri, which is a bit dimmer and just a tad closer to us. How cool is that? Did you know that Sirius, the brightest star visible from our planet, besides the Sun, has a mysterious, faint white dwarf companion? It's a fascinating cosmic duo that sparks curiosity and wonder about our universe. Since the days of Hipparchus back in the 2nd century BC, astronomers have been using a fascinating system known as magnitudes to gauge the brightness of stars. It's a captivating journey through time that showcases how we've measured the cosmos. Stars that we can see are grouped into 6 different magnitudes. The first magnitude includes the brightest stars we can spot, while the 6th magnitude features the faintest ones that still catch our eye. In 1836, John Herschel made a groundbreaking discovery. Stars classified as first magnitude shine 100 times brighter than those in the 6th magnitude. Fast forward to 1850, and George Pogson, another brilliant astronomer, revealed that each step up in magnitude means a drop in brightness by a factor of 2.5. Fascinating, right? Check out these fascinating results from the relation 2 to 5555100. To break it down, an increase of 5 magnitudes from the 1st to the 6th means there's a staggering 100-fold decrease in brightness. How cool is that? Did you know that a star of 2nd magnitude shines 2.5 times dimmer than a 1st magnitude star? And here's a fun fact. A star with a magnitude of m is actually 2.5 raised to the power of m minus 1 times fainter than a 1st magnitude star. How cool is that? Astronomers stick to some pretty quirky units, like parsecs and magnitudes for traditional reasons. Much to the chagrin of their fellow scientists, especially those in the physics realm, they steer clear of the trendier units. Interestingly, while most scientists have embraced the use of meters and kilograms, astronomers stick with centimeters and grams. They argue that the distinction between centimeters and meters, or grams and kilograms, is insignificant when dealing with the vast scales of astronomical measurements. What are the advantages of transitioning from one unit system to another, especially when both incorporate complex numbers? Astronomers often cling to traditional units, or opt for newly created ones that add complexity when dealing with astronomical quantities. When we talk about distances in space, we often use astronomical units, parsecs, or light years. For masses, we refer to them in terms of XM8, which means X times the mass of our Sun. And for luminosities, we use YL8, indicating Y times the luminosity of the Sun. It's a fascinating way to understand the vastness of the universe. Did you know that matter in bulk comes in 4 fascinating states? That's right. We have solids, liquids, gases, and even plasma. Each state has its own unique characteristics that make it truly interesting to explore. Solids are fascinating structures. They're rigid and held together by powerful interatomic electrical forces with atoms that vibrate around fixed points. Let's dive deeper into the science behind these incredible materials. Liquids, gases, and plasmas represent dynamic states where atoms enjoy greater freedom of movement, breaking free from the constraints of interatomic forces. As the temperature of a solid heats up, the atoms start to vibrate with more energy, and they begin to slide around each other, either individually or in groups. It's a fascinating dance of movement that happens at the atomic level. The solid has transformed into a liquid. When temperatures rise, the atoms start to vibrate intensely, breaking their bonds and transforming into a gas filled with freely moving particles. It's a fascinating process that showcases the dynamic nature of matter. When temperatures soar to several thousand kelvins, something fascinating happens. The atoms become ionized, transforming the gas into a plasma filled with free electrons and partially or fully ionized atoms. It's a wild state of matter. That's essential to understanding the universe. Did you know that the majority of matter in the universe exists in a fascinating state called plasma? It's a mind-blowing fact that really makes you think about the cosmos. Text. In the closing lines of Arthur Eddington's The Internal Constitution of the Stars, he notes, sensitive experiments have succeeded in detecting only a fraction, about half, of the expected neutrino flux reaching the Earth. This highlights the ongoing quest in modern science to replicate the Sun's nuclear fusion energy right here on our planet. We're diving into an exciting concept here. Imagine harnessing deuterium, a form of heavy hydrogen that's abundant in our oceans, as a game changer. This approach could help us sidestep some of the challenges we face with the slow and weak interactions in the proton-proton chain. It's a fascinating twist in the quest for energy solutions. However, the initial challenge, the electrical repulsion between protons, still persists. Even though deuterons are eager to react when they come together, unleashing a burst of nuclear energy, the challenge of overcoming their electrical repulsion barriers remains a significant hurdle. Many people think that the secret to achieving fusion lies in mimicking the processes of the stars. So we need to crank up the heat on the deuterium gas to a staggering tens, even hundreds of millions of Kelvin. The hydrogen bomb, utilizing a fission bomb as its trigger, has already unleashed an uncontrolled release of thermonuclear energy. If the Sun were made up entirely of heavy hydrogen, it would also face an explosive fate. We need a safe and systematic approach to harnessing fusion energy. The challenge of keeping gas contained at those high temperatures for an extended time, William Thomson, on the age of the Sun's heat. This thought-provoking statement invites us to ponder the origins of our Sun's energy and the laws of nature that govern it. Join us as we dive deeper into the mysteries of the universe and explore the science behind our star's incredible journey through time. Building on a fascinating concept introduced by the German scientist Hermann von Helmholtz, it was suggested that the Sun replenishes its emitted energy through a gradual process of gravitational contraction. He discovered that the age of the Sun, using this method now referred to as the Helmholtz-Kelvin timescale, is roughly 20 million years. Before we unlocked the secrets of nuclear energy, gravitational contraction was widely seen as the most logical and intuitive explanation for how the Sun and stars shine so brightly. Imagine a sun that's just 20 million years old. While that might seem like a long time in some circles, it's actually a blink of an eye when you consider the vastness of geological history and the intricate dance of biological evolution. This sparked some serious debates among physicists, geologists, biologists, and paleontologists, especially as the late 19th century rolled around. The clash of ideas was nothing short of intense. The groundbreaking discovery of radioactivity, along with the stunning realization that our solar system is billions of years old, finally put an end to the debate. The Helmholtz-Kelvin timescale plays a crucial role in understanding stellar structure theory. In this fascinating discussion, we explore how radiant energy travels from the core to the surface of the Sun. By multiplying the Sun's luminosity by this timescale, we uncover the incredible heat content of our star. Join us as we dive into the science behind this stellar phenomenon. During the 20th century, scientists made some incredible discoveries, observing a multitude of supernovas across different galaxies. For a brief moment, each supernova can outshine every star in its galaxy, creating a spectacular cosmic event that captivates our imagination. Over the past 2 millennia, we've documented 14 supernovas in our galaxy, with the most recent sighting occurring in 1604. Fascinating, right? One of the most renowned supernovas in history occurred in 1054 within the constellation Taurus. This spectacular event was documented by Chinese astronomers, and today its remnants can be found in the stunning Crab Nebula. In 1572, Tycho's star lit up the night sky in the constellation Cassiopeia, while Kepler's star made its mark in 1604 within the constellation Serpens. Fascinating celestial events that continue to intrigue us today. Back in 1572, the brilliant Tycho Brahe penned an incredible observation. One evening, while I was gazing at the familiar celestial vault, I was struck with awe as I spotted a dazzling star of extraordinary size near the zenith in Cassiopeia. This moment highlights how much of our past cosmological thinking has revolved around the center and edges of the universe, reflecting our ongoing fascination with the principles of location and containment in our understanding of the cosmos. The location principle dives into the fascinating aspects of the cosmic center, while the containment principle explores the intriguing boundaries of the cosmic edge. These principles guide us away from the traps that previous cosmologists stumbled into. The containment principle of the physical universe tells us that it encompasses all things physical and excludes everything beyond that. Fascinating, right? This principle stands as the cornerstone of the physical sciences, particularly in the realms of chemistry and physics. For some, this principle seems so straightforward and clear that it barely warrants a mention. Yet for others, it represents a bold and controversial philosophy that sparks intense debate. Before we jump to conclusions about this principle being too basic or even outrageous, let's take a deeper look at what it really means. Modern scientific cosmology dives into the vast physical universe, encompassing everything that is tangible while leaving the non-physical behind. Physicality is a concept that stretches far beyond what we typically think is appropriate, opening up a wide range of interpretations and discussions. It includes all measurable elements linked by ideas that can be challenged. Atoms and galaxies, cells and stars, organisms and planets. These are the incredible physical entities that make up our fascinating universe. Imagine particles that dance between being waves and tiny objects, atoms with their swirling electron waves, and DNA that carries the blueprint of life. Picture fields and waves zipping through the cosmos, the intricate voids of the vacuum, and the fascinating aspects of spacetime shaped by special relativity. Consider the dynamic, curved spacetime, from general relativity and the vast universe that stretches out before our eyes. These are the incredible physical phenomena that make up our reality. But wait, there's even more to uncover. As beings with bodies and minds, we find ourselves navigating the confines of the physical universe. Space and time aren't merely empty canvases where the universe has been placed. If they were, we could simply find spots in space and time that the universe doesn't fill. Spacetime, that fascinating four-dimensional blend of space and time, isn't just an empty container. It's a dynamic and tangible continuum that shapes our universe in profound ways. It's a fascinating continuum that holds a unique reality within it. Space and time play a dynamic role in the grand design of the universe. They are integral to the physical realm and do not reach beyond its boundaries. The universe is a fascinating concept that encompasses both space and time, yet intriguingly, it exists beyond the confines of space and time. Let's dive deeper into this mind-bending idea. If you subscribe to the idea of a non-physical realm like heaven, we can't stretch our understanding of space and time to encompass heaven because doing so would pull it into the physical universe, subjecting its existence to the scrutiny of scientific investigation. Dynamic properties reveal the fascinating physical essence of space, or more accurately, space-time. Did you know that empty regions of space actually interact and influence each other? It's a fascinating concept that opens up a whole new realm of possibilities in our understanding of the universe. This process truly captures the heart of general relativity. In the grand tapestry of the cosmos, past universes unfolded their stories on the epic stages of space and time, where the drama of existence played out in all its glory. In today's physical universe, space and time take center stage as the main players. Who can question the undeniable presence of space, or space-time, when it influences the tides, orchestrates the moon's dance around the Earth, and governs our planet's orbit around the Sun? It's a force so powerful that it can rip apart careless astronauts and their spacecraft near neutron stars and black holes. Imagine a universe that is both limited and limitless at the same time. How fascinating is that? Imagine the smooth, rounded surface of a sphere. It's a perfect analogy that's easy to picture in your mind. The surface stretches endlessly, with no boundaries in sight. Imagine an ant making its way in a straight line across the surface of a spherical watermelon. Surprisingly, it finds its way back to where it began, all without ever hitting an edge. How fascinating is that? Imagine a cosmic explorer journeying through a universe that's both finite and uniform, where every path leads back to the beginning. It's a mind-bending concept that invites us to ponder the nature of space and time. There are those who will argue that the containment principle leaves out everything that truly matters. Let's dive into the fascinating realms of our souls, minds, and consciousness. What about the incredible depth of our inner mental world? It's a topic that sparks curiosity and invites exploration. How do they fit into the bigger picture? The answer is clear-cut. They simply aren't found anywhere. At the very least, only their physical counterparts, like chemical activities, really make the cut. The wonders of life can be boiled down to the fascinating biochemistry of neurons in our brains. When addressing those who seek a tidy explanation of the spiritual, psychological, and physical realms, we need to clarify: you're mixing up the universe with the universe. The unknown universe encompasses everything, including our thoughts. The known physical universe is limited to what we can touch and see, including our brains. Experts in mathematics, physics, biophysics, and chemistry have shaped our understanding of the physical universe. If you're not satisfied with it, despite its remarkable achievements, it's time for you to create your own universe. It's important to note that modern cosmology primarily concentrates on a model of the physical universe. The universe acts like a mysterious curtain, hiding the secrets of the unknown from us. Wow, what an incredible mask we have here. The brilliance and creativity of the most remarkable minds in the history of science have come together to create this incredible work. As I stand in awe of the grand physical university, I can't help but question why so many, even those in the scientific community, have confused this latest facade for the true essence of the university puzzle. In the fascinating realm of the ancient Mediterranean, the atomists and Epicureans boldly embraced the concept of a universe that is innate, centerless, and edgeless. Their revolutionary ideas continue to spark curiosity and debate today. Aristotelians and Stoics promoted a structured universe with a clear center and boundaries. The ongoing debate has always centered around one crucial issue: the mystery of the cosmic edge. Text. Back in the 5th century BC, Archytas of Tarentum, a Pythagorean soldier philosopher and buddy of Plato, threw out a mind-bending riddle. What happens to a spear when it's launched beyond the edge of the universe? Does it bounce back? Or does it just disappear from our reality? This question really gets you thinking, doesn't it? This riddle reveals a fascinating contradiction. How can something that defines its own limits not be part of the universe? For over 2 millennia, some of the brightest thinkers have grappled with this puzzle, and Archytas's riddle has significantly influenced the evolution of cosmology throughout history. In the 4th century BC, Epicurus stated, "Democritus of Abdera said that there is no end to the universe, an outside power did not create. Moreover, these are endless. For that which is bounded has an extreme point, and the extreme point is seen against something else." Lucretius the Epicurean, influenced by the riddle of Archytas, wrote in the 1st century BC in his magnificent poem De Rerum Natura, "It is a matter of observation that another limit one thing. Air demarcates the hills, and the hills demarcate the air. The land sets bounds to seas, and the seas to every land. But there is nothing outside to limit it." He asked those who believed in a bounded universe, "Suppose for a moment that the whole of space was bounded, and that someone made his way to its uttermost boundary and threw a flying dart. Do you choose to suppose that the missile, hurled with might and main, would speed along the course on which it was aimed? Or do you think something would block the way and stop it? You must assume one alternative or the other. With this argument, I will pursue you. I will ask, what happens to the dart? No matter where you draw the line," Lucretius responded to the atomist, "understand that the universe knows no bounds in any direction." In the 6th century AD, Simplicius echoed this thought. In his fascinating exploration of Aristotelian physics, Archytas poses a thought-provoking question. If I stand at the edge of the heavens, can I extend my hand outward? It seems absurd to think I couldn't. If I can, then what lies beyond must be either a body or space. This leads us to the idea of endless extension. In his dialogue, The Infinite Universe, penned during his time in England, Bruno presents an intriguing argument through the character Berkio, who embodies Aristotelian thought. One might argue that if someone reaches beyond the celestial sphere, their hand wouldn't occupy any position in space, and thus wouldn't exist. However, Philotheo, representing Bruno himself, counters that space, both within and outside the universe, is continuous and identical. So, no matter the surface, I must always inquire, what exists beyond? If the response is nothing, we can refer to it as void or emptiness. This void or emptiness is boundless and immeasurable, yet it does have an endpoint. Interestingly, this concept of emptiness can be more challenging to grasp, than the idea of a vast, inherent universe. This commentary by Simplicius, a Neoplatonist, on Aristotelian physics remained relatively obscure until it was translated into Latin in the 16th century. Text. Imagine a world where a powerful poem lost to time resurfaces in 1417 within the walls of a monastery. This remarkable work by Lucretius captured the attention of brilliant minds like Nicholas of Cusa, Giordano Bruno, Thomas Diggers, and William Gilbert, sparking discussions and ideas that would shape the future. Join us as we explore the impact of this literary gem and its journey through history. In a fascinating universe, everything is intricately connected to both the cosmic center and its edges. This captivating arrangement, where every element has a definitive place, was the cornerstone of pre-Copernican cosmology. Over time, groundbreaking astronomical discoveries shattered the idea of a cosmic center, while the intriguing riddle posed by Archytas put an end to the belief in a cosmic edge. Have you ever pondered the concept of an innate universe? It might just have come about as a fascinating answer to the cosmic edge riddle, possibly in the way Archytas presented it, or even in some earlier lost form. Let's dive into this intriguing idea together. Atomists and Epicureans had a fascinating perspective on the universe that might surprise you. They were completely unbothered by the riddle of existence, confidently asserting that space is infinite. Imagine a cosmos packed with stars, planetary systems, and vibrant life, stretching endlessly to the very edge of the universe. It's a mind-blowing concept that invites us to ponder our place in this vast expanse. Stay tuned, because what we're about to uncover is how tackling the cosmic edge mystery led to the intriguing puzzle of our night sky, a key player in the fascinating journey of cosmology. In the fascinating realm of ancient cosmology, the universe came to a dramatic halt, marked by a striking wall-like edge. In the fascinating world of mythology, the universe is frequently illustrated as being encased in a shell, or as a grand cavern surrounded by mysterious dark walls. Eventually, that boundary transformed into the realm of fixed stars in the Aristotelian universe. Did you know that even Johannes Kepler thought the universe was surrounded by a mysterious dark cosmic wall? He had some intriguing ideas about why the night sky appears so dark. Tune in to explore this fascinating concept. Kepler proposed that in a limitless universe filled with stars, the night sky wouldn't be dark at all. Instead, it would be illuminated by a dazzling array of starlight. It's uncertain whether Kepler ever cracked the cosmic edge mystery. When faced with a wall-like edge, the spear has two options. It can either bounce back or go right through it. Epicurean critics dive into a fascinating debate, claiming that the first option is a no-go since something that defines the limits of space can't possibly be unbounded. Meanwhile, the second option raises an intriguing point. What if an edge simply doesn't exist at all? In the later iterations of the Aristotelian universe, particularly during the Neoplatonic and medieval periods, the concept of space didn't just come to a sudden halt. Instead, it faded away gradually, starting from the lunar sphere. Fascinating, right? As we journey outward from Earth, the physical world gradually shifts into a captivating etheric realm. In the medieval perspective, the outer etheric celestial realm was enveloped by the Empyrean, a divine space inhabited by God. There are two intriguing possibilities to consider. What happens to a physical body as it moves away from Earth? One scenario is that the body's earthly elements stay the same and eventually return to Earth, much like a stone thrown into the air that comes back down. The other possibility is that the body transforms into etheric elements, leading to a natural motion that is circular around the Earth rather than just going up and down. Fascinating, right? In the medieval universe, there existed a sharp boundary that changed everything. The powerful notion of, "with argument I shall pursue you," faded away as the pursuer ventured into an ethereal outer realm where physical arguments simply held no weight. It's a fascinating shift that challenges our understanding of reality. This cosmic edge felt like the ground slowly melting away into an endless marshland, creating a surreal and captivating landscape. The medieval response to the riddle just doesn't cut it anymore. Insights reveal that the physical realm remains distinct and does not dissolve into a non-physical dimension, even at vast distances. Imagine a Stoic cosmic edge, a universe filled with a finite array of stars, all set against the backdrop of an infinite, starless void. It's a fascinating concept that invites deep reflection and exploration. The Stoic edge was as sharp as the precipice of a towering cliff. It split the universe into a dazzling inner cosmos filled with stars, and an endless outer space that stretches on forever. In this intriguing scenario, the solution to the cosmic edge riddle was surprisingly simple. By throwing the spear, the cosmos expanded, pushing its outer limits even further. In the early days of Stoicism, thinkers introduced the concept of an innate void, adding it to the Aristotelian sphere of stars. This move was likely a clever response to the intriguing riddle posed by Archytas. Inescapably, the medieval universe transformed into a grand Stoic cosmos filled with stars, while the inherent void evolved into the transcendent realm of God. This cosmic picture quickly gained a massive following. Picture this: Isaac Newton's groundbreaking perspective on the universe during his formative years at Cambridge. Fast forward to the late 18th century, and we find ourselves captivated by William Herschel's stunning vision of the Milky Way cosmos. Then, we dive into the Victorian universe of the 19th century, a concept that held sway until the early decades of the 20th century. What a journey through time and thought. Imagine this. You could take a journey in your mind, venturing beyond the Milky Way. Picture yourself looking back, witnessing a breathtaking panoramic view of the entire material universe. How incredible is that? Recent observations suggest that the material universe stretches out in incredible distances beyond our Milky Way, and intriguingly, there's no indication of a sudden boundary. Exploring the universe. When someone first dives into the fascinating world of cosmology, they often envision the Stoic cosmic picture. Imagine the universe as this incredible, vast spherical cloud of galaxies, constantly expanding through the cosmos, complete with a center and an edge. It's a mind-blowing concept that really makes you think about our place in the grand scheme of things. This straightforward image, sadly, misses the mark and goes against the containment principle. Space isn't just some empty container where the universe hangs out. It's a dynamic, physical entity that expands right alongside the universe itself. Space is a fundamental aspect of the universe, and it has its limits that cannot be surpassed. In a fascinating twist to what we might expect from a Stoic perspective, the Big Bang didn't just happen in a specific spot in space. It actually filled the entire cosmos. How mind-blowing is that? If space knows no bounds, then the Big Bang was truly a part of its essence. An innate universe is forever innate. It cannot transform into something finite. No matter where we are right now, let's hit pause and take a thrilling trip back in time to explore our origins at the moment of the Big Bang. Picture this: a centerless and edgeless three-dimensional space that stretches the limits of your imagination. It's a concept that's not too hard to wrap your head around, right? Envisioning a night sky that has no center and no edges in three-dimensional space is quite a challenge. Imagine a two-dimensional surface that has no center, no edges, and is finite. It's a fascinating concept to explore. Imagine a spherical surface that stretches infinitely in all directions, with no center or edge to confine it. It's a fascinating concept that challenges our understanding of space. There are no cosmic edges in space. We can't embark on a journey to the edge of existence, much like Dante and Beatrice in the Divine Comedy, to take in a breathtaking panoramic view of the universe. 8.4. Imagine a universe that's constantly growing. Instead of galaxies zooming away from us, they're actually just hanging out in space, while the very fabric of space itself stretches out, much like the surface of a slowly inflating balloon. How cool is that? Later on, we explore how the expansion of space pulls galaxies further apart from each other. Just like space, time is a tangible entity, and it's all wrapped up within the walls of the university. Yet it reaches beyond the university, touching on a cosmic edge that transcends time itself. Let's not get caught up in pondering what the universe is like before or after time wraps up. Just like we shouldn't be curious about what it looks like from outside the bounds of space. These kinds of questions challenge the containment principle and suggest that the physical universe encompasses all things physical. Cosmogony, which refers to the fascinating process of creating cosmic progeny, explores the origins of incredible astronomical structures like planets, stars, and galaxies. It's a captivating topic that delves into the very beginnings of our universe. It dives into the fascinating origins of the elements and the very essence of life itself. The limitations imposed on cosmogony by containment are fundamental. Everything in existence has to fit within the bounds of the universe's size. Let's dive into an intriguing topic: the fascinating world of nucleochronology. This field explores the origin and history of elements through a variety of dating techniques. Join us as we unravel the mysteries of the cosmos and how these methods help us understand our universe better. In the early days of the universe, when everything was young, dense, and sizzling hot, the light elements we know today, primarily deuterium and helium, were forged from protons and neutrons during the incredible event known as the Big Bang. Stars played a crucial role in creating most of the chemical elements we know today, and they released these elements into the cosmos during spectacular supernova explosions. Long before our solar system came into existence, the cosmos was alive, with stars that forged the very elements that make up our planet Earth. Did you know that most heavy elements are actually radioactive? That's right. When they form, they start a fascinating journey of decay into daughter elements. It's a wild ride through the atomic world. Did you know that uranium-235 has a staggering half-life of 4.5 billion years? That's right. It slowly transforms into lead over an incredibly long period of time. Fascinating, isn't it? Understanding the speed at which radioactive elements decay and measuring their current relative abundances allows us to unlock the secrets of the age of the Earth, the solar system, and even our galaxy. According to these fascinating studies, we discover that our solar system is about 4.6 billion years old, while the galaxy itself has an impressive age of around 15 billion years. Cosmologists believe that the universe has been expanding for somewhere between 10 and 20 billion years. But here's the twist. From the late 1920s all the way through to the mid-1950s, scientists pegged the age at just over 1 billion years. Imagine a universe that's younger than our own Earth, breaking free from its confines. For 25 years, this age paradox has been the talk of the town in cosmology, sparking debates and igniting curiosity. Tune in as we dive into this mind-bending concept. There were efforts to sidestep the paradox, like the hesitation universe theory, which suggests that expansion was sluggish for an extended time in the past, and the steady-state model, which proposed an inherent past. Georges Lemaitre and George Gamow, two pioneering cosmologists who championed the Big Bang theory, argued that this monumental event was responsible for creating most of the elements in our universe. This idea turned out to be wrong, but it had one significant advantage. It inspired Gamow and his team, Ralph Alpher and Robert Herman, to explore the concept of a hot, early universe. This exploration led them to predict the existence of cosmic background radiation nearly 20 years before it was actually discovered. The steady-state concept turned out to be incorrect, but it had a significant advantage. Steady-state cosmologists rejected Big Bang nucleosynthesis, which led them to demonstrate that all heavy elements are produced in stars. Let's take a moment to celebrate the trailblazers who shaped our understanding of stellar nucleosynthesis. We're talking about the brilliant minds of Alistair Cameron, the dynamic duo Margaret and Geoffrey Burbidge, the incredible William Fowler, and the legendary Fred Hoyle. These pioneers truly revolutionized the field. Revised estimates of extragalactic distances, pioneered by Walter Baade and Alan Sandage in the 1950s, and further refined by others since, have significantly expanded our understanding of the universe's size and age. It's fascinating to think that we can fit the ages of chemical elements, our planet, the solar system, stars, and even galaxies, into the timeline of a Big Bang-type universe. What a mind-bending concept. What are the fascinating connections between our universe and the existence of... Throughout the ages, stories and beliefs have championed the concept of a universe that's been thoughtfully crafted. The idea that the universe was purposefully crafted to be a home for humanity dates back to the earliest creation myths. The design argument suggests that the presence of a supreme designer is evident in the incredible cosmic design and the breathtaking wonders of nature all around us. In the 18th century, the design argument took on a fresh and definitive shape, known as deism, emerging alongside the groundbreaking ideas of the Cartesian and Newtonian world systems. Theism is this age-old belief that a supreme being is behind the creation and management of the universe. Imagine a belief system where a supreme being crafts a universe so flawlessly designed that it runs on its own, without the need for any supernatural intervention. This concept invites us to explore the intricacies of existence and the wonders of creation in a whole new light. Back in 1687, Thomas Burnet, a clergyman, shared some fascinating thoughts in his work, Theory of the Earth. He suggested that a true artist is one who creates a clock that ticks away perfectly on its own, rather than one that requires a nudge every hour to keep going. This clock analogy became a popular tool among 18th century deists, who used it to bolster the design argument. It's a compelling way to think about the universe and its intricate workings. Back in 1802, Archdeacon William Paley made a compelling case in his book Natural Theology. He suggested that the intricate designs of our eyes and hands are too complex to have arisen by mere chance in nature. It's a fascinating argument that still sparks debate today. He penned, "I found a watch on the heath, leading to the conclusion that the watch must have a maker. There must have existed at some time and place an article or artisans who crafted it for a common purpose, which we find it actually serves, who fully understood its design and intended use. However, as time progressed, the evolution of science revealed that the forces of nature are far more insightful than Paley had imagined. In the Bridgewater Treatise, crafted by 8 distinguished authors to highlight the power, wisdom, and goodness of God as manifest in the creation, chemist William Prout pointed out in 1834 that the peculiar behavior of water expanding when it freezes serves as a remarkable illustration of design in nature. It's as if this phenomenon was intentionally created to fulfill a specific purpose, showcasing the intricacies of our world. Prout pointed out a fascinating scenario. If water didn't expand when it froze, and ice remained solid, our oceans would turn into a solid block of ice, rendering life on Earth utterly impossible. Can you imagine the implications of that? It's a chilling thought. Science has gradually unveiled a mind-blowing world filled with incredible complexity, driven by powerful forces that leave us in awe. Natural selection, the process where individual traits that enhance survival and reproduction become more common in a breeding population, explains the remarkable development of our eye and hand. It's a fascinating concept that showcases the wonders of evolution. The wonders of the physical world extend beyond just the amazing structures we see, like our eyes and hands. They dive deep into the fundamental properties at the atomic and subatomic levels, which astonishingly come together to create a universe that supports life. It's a fascinating journey into the very fabric of existence. In 1913, Lawrence Henderson, a prominent scientist from Harvard University, shared some groundbreaking insights in his work, The Fitness of the Environment. He stated, "The fitness of the environment results from characteristics that constitute a series of maxima, unique or nearly unique properties of water, carbonic acid, and the compounds of carbon, hydrogen, and oxygen. The oceans are so varied and nearly complete among all things involved in this issue that together they undoubtedly create the greatest possible fitness." Fast forward to today, and advancements in physics reveal that the remarkable fitness of the molecular world Henderson described stems from fundamental design at the atomic and subatomic levels. This connection between the micro and macro worlds is truly fascinating. Let's talk about multiple universes. We've touched on the concept of universes, where each one serves as a unique model of the universe. Imagine not just one, but a multitude of physical universes, each one self-contained and completely isolated from the others. It's a fascinating idea that opens up so many possibilities. Imagine a scenario where the fundamental constants of nature vary from one universe to another. Universal constants of nature refer to those fundamental and mysterious elements that govern our universe. Think about the speed of light, denoted as c, the universal gravitational constant g, the electric charge I of protons and electrons, Planck's constant h, and the masses of subatomic particles. These constants are the building blocks of everything we observe in the cosmos. Imagine a fascinating collection of universes, each one showcasing every possible combination of nature's constants. It's a mind-bending ensemble that opens up endless possibilities. Every universe acts like a fascinating laboratory, allowing us to dive into the intriguing outcomes of tweaking the constants that set them apart from our own reality. In some scenarios, gravity is a heavyweight champion, while in others, it's more of a lightweight. And then there are those wild cases where gravity flips the script and becomes repulsive. How fascinating is that? In this fascinating cosmic landscape, we encounter strange universes where the scale of H is so immense that quantum mechanics plays out on a grand scale. While in others, it's so tiny that those quantum effects barely make a ripple. Even the smallest tweaks to the fundamental constants can lead to massive shifts in the cosmic landscape. Even the tiniest shifts in the fundamental constants of C, H, and E can lead to astonishing transformations in the very fabric of atoms and their nuclei. In the vast multiverse, stable atomic nuclei are a rare phenomenon. Most universes are dominated by hydrogen gas, missing out on the crucial elements like carbon, nitrogen, and oxygen that are vital for the emergence of organic life. It's a fascinating glimpse into the diversity of existence beyond our own universe. Even the tiniest tweaks in the values of C, G, H, E, and the masses of subatomic particles can lead to dramatic shifts in how stars are structured and evolve over time. It's fascinating how such small changes can have such a big impact. In the vast expanse of the multiverse, it's fascinating to discover that nearly all universes are devoid of stars. And for those that do have them, many feature non-luminous stars, or incredibly bright ones, whose lifespans are far too brief to support the development of life as we know it. What does this mean for the possibilities of life beyond our own universe? Let's dive into this cosmic mystery. Life forms, the incredible organisms we know and love, are made up of a mix of chemical elements and thrive in environments like cozy planets warmed by enduring stars, where they can begin their journey and evolve over time. A fascinating study of the cosmic ensemble reveals that only universes that closely resemble our own meet these intriguing requirements. Our very existence hinges on the precise values of the constants of nature as we observe them. If they were different, we simply wouldn't be here. The accidentals of nature, as Aristotle put it, are finely tuned at the most fundamental level. Many other universes with their unique designs are devoid of stars and life. Our universe is strikingly similar to the vast ensemble of possibilities out there, and it might just be the only one that harbors life. How fascinating is that? The exercise wraps up by highlighting that life as we know it wouldn't be possible if the fundamental constants of physics were altered. What's the deal with the constants of physics being so finely tuned? Let's dive into this intriguing question. Is the fine-tuning intentional, or just a happy accident? Could there be an intriguing, yet-to-be-discovered theory that links and clarifies why the constants of physics hold the specific values we observe? Let's dive into this fascinating question. So here's the deal. The fundamental constants of physics either seem to be fine-tuned on purpose to support life, think of it as a theistic principle, or they just happen to align perfectly by chance. That's the Anthropic principle for you. Fascinating, right? In the first scenario, we can set aside the collection of universes. In the second, we definitely need to keep it around. In the realms of Judaism, Christianity, and Islam, there's a fascinating idea that God meticulously crafted our perfectly tuned universe, shaping it as a unique space specifically for life to thrive. It's a thought-provoking concept that invites us to explore the divine intentions behind our existence. What makes the university what it is today? It's all part of the divine design, crafted for the betterment of life itself. Deism places a greater emphasis on the concept of design compared to theism. This perspective is often the first that comes to mind. We can set aside all the other universes in this cosmic collection. These actions were simply practical steps. That helped us understand how our universe is perfectly set up for life to thrive. Let's dive into the fascinating concept of the Anthropic principle. It suggests that the universe is one of a kind, simply because we are here to observe it. How cool is that? Text. Let's dive into the fascinating world of the Anthropic principle. First brought to light in a scientific context by Robert Dicke back in 1961. This concept was further refined by Brandon Carter, and has since sparked discussions among countless thinkers and writers. It's a topic that really gets the mind racing. In Twelfth Night, the clown only shared part of the truth when he said, "That's what it is." The full truth goes deeper. I exist as I am. Therefore, what exists, exists. Back in 1974, Brandon Carter coined the term Anthropic principle, explaining that what we can observe is limited by the very conditions that allow us to be here as observers. He called this straightforward idea the weak Anthropic principle. Let's dive into the intriguing debate surrounding the strong Anthropic principle. Some have boldly denied its controversial stance, suggesting that the universe possesses the essential properties for life that may have existed at some point in its vast history. What does this mean for our understanding of existence? Tune in as we explore this fascinating topic. The robust version of this principle leads us down a fascinating maze of philosophical questions, and we've chosen to set aside the theological aspects under the banner of theistic principle. What's the purpose of the university being there? Text. Have you ever found yourself pondering the big questions about our universe? Like, why is it the way it is? Or even more intriguingly, why do atoms exist at all? These existential inquiries really get us thinking, don't they? There are three possible responses. Let's kick things off with a thought-provoking question. How do atoms work? This replaces our original inquiry and dives right into the science of it all. In the realm of science, we often see functional questions stepping in to take the place of those deeper existential inquiries. The second response revolves around the idea that a divine force shapes the universe, crafting a cosmic design that harmonizes perfectly with life itself. This theological response puts an end to scientific exploration. Counter-arguments raise even more intriguing questions like, why did God create the world in this manner? And who is responsible for making and designing God? By stating that the nature of God is beyond rational inquiry. Third response. The Anthropic principle. Things are the way they are because we exist. Our existence determines the cosmic design. We would not be here if the design were different. Different universes distribute nature's accidentals with random values. Why is the university there? This is due to our very existence. But why do we exist? Our existence is due to the inherent nature of the universe. The universality of the argument is broken in the theistic principle at the price of introducing a supreme being, and in the anthropic principle at the cost of introducing an ensemble of universes. Human existence does not limit either principle. All other creatures on Earth are manifestations of a newly tuned universe. Wildflowers do not exist in other universes. When given a widower, one is also given our universe's face. Intelligent creatures impose no more constraint on the universe than wildflowers. The fundamental constants have values that are either intentional, theistic principle, or fortuitous, anthropic principle, and otherwise inexplicable. But science has always advanced by explaining what was previously considered inexplicable. Perhaps in the future, the constants of nature will have rationally explained values that are neither intentional nor fortuitous. We prefer anthropic or theistic ideas, ignoring the whole subject and concentrating on functional issues. On the one hand, we have the idea that our universe is one of a multitude of universes, and exists in its current form because we are here. On the other hand, we have the idea that our universe is naturally designed, which limits further scientific inquiry. Given a choice between a supreme being beyond rational inquiry and a wasteland of mostly dark and barren universes, most people would choose the former. The laws of nature are the patterns and rules that help us perceive harmony and order in the universe. They reveal the fundamental patterns of space-time and how it breaks down into three-dimensional space and one-dimensional time. Often the laws are mathematical codifications that mimic the structure of the world, as observed by the human mind. We hold on to them until they contradict observation, at which point we modify or discard them. The known laws were different in the past and no doubt will be different from today's in the future. Most branches of science study objects ranging in size from atoms to galaxies. Atoms are typically 10 centimeters in size, and galaxies are typically 10 centimeters, 100,000 light-years in size. Galaxies are 1,031 times larger than atoms. This entire range of sizes covers 31 orders of magnitude. Most phenomena of interest in science lie in this middle realm of physics. Almost everything is explained by electromagnetic forces at the atomic end of the scale. And at the galactic end, almost everything is explained by gravitational forces. By moving up 5 orders of magnitude to a typical cosmic size of 10 to the power of 28 centimeters, 10 billion light-years, and down 5 orders of magnitude to 10 centimeters, a typical subatomic size of 10 to the power of 13 centimeters, the size of a nucleon. We leave the middle realm and enter the less familiar outer realms of physics. At the upper end, in the cosmic realm, gravity continues to be the ruling force in the guise of curved dynamic spacetime. However, other forces, both weak and strong, join electromagnetism in the subatomic realm at the lower end. The universe seems oddly asymmetric, simplicity in the cosmic realm and complexity in the subatomic realm. However, the electromagnetic and weak forces are the twin aspects of an electroweak force, and both were once united at high energy in the early universe. Electroweak forces are also twin aspects of a hyperweak force, and were once united at an even higher energy at an earlier time in the very early universe. The asymmetry between the atomic and cosmic realms may be apparent, but it is not real. After all, we must not forget that the universe uses atomic particles and is at least as complex as the particles themselves. Doctrines of internal and external relations. The university has yet to discover the physical properties that unify particles and the cosmos. This idea is implicit in the long-standing bootstrap principle. The bootstrap principle states that all things are immanent within one another. Anaxagoras had the idea when he said, "In everything there is a portion of everything." The physicist Gyoré Chu said, "Nature is as it is because its entirety is the only possible nature consistent with itself. How things are on the largest scales determines how they are on the smallest scales, and vice versa. The macrocosm is reflected in the microcosm, according to Gottfried Leibniz's theory. This theory answers Victor Hugo's question. Where the telescope ends, the microscope begins. Which of the two has the grander view? It might be that in an ultimate sense, both views are equivalent. In the 18th century, Bishop Berkeley proposed a bootstrap principle, arguing that the distribution and masses of all other bodies in the universe determine the inertia of a body. In the 19th century, the universe proposed a similar idea, and this bootstrap argument, now known as Mach's principle, inspired Albert Einstein. The philosopher Alfred Whitehead referred to this arrangement as the doctrine of external relations. Everything operates in a push-pull manner which explains the universal human experience of living in a competitive environment. Existential questions, such as why all electrons have the same electric charge, are not easily answered in the atomist worldview and tend to be suppressed. The atomist world picture answers functional questions that start with how much more readily, which pertains to the movement of objects. We see signs of internal relations emerging in physics. Newtonian gravity was an external relation of the push-pull kind. General relativity is a much subtler scheme of things. Gravity, as we know it, vanishes and is replaced by the dynamic curvature of spacetime exhibiting properties of internal relationship. However, despite our tendency towards abstraction, we still refer to gravity as a force despite its disappearance. Quantum mechanics uncovers a strange world of internal relations. As Richard Feynman said, nobody understands quantum mechanics. An excited atom in the depths of space decays, and while decaying, emits a photon wave in all directions. 1,000,000 years later, 1,000,000 light-years away, the wave enters a telescope on Earth and creates an electrical signal in a detection instrument. Instantly, the entire spherical wave throughout space collapses into the photon emitted by the decaying atom and received at the detector. The photon can be watched only once. Therefore, the entire wave, spread out over millions of light-years, collapses at the moment of observation of the photon. In the push-pull world of external relations, a world invented long ago by primitive humans, such behavior is mysterious. The old atomist principle tells us how, but not always why. The implicate principle tells us why, but not always how. Perhaps, in a hypothetical world of intelligent and non-aggressive creatures,